Hello there, and welcome to Sleepy Cosmic Podcast, where we wander beneath velvet skies, following ancient light on its unhurried path through time. If this kind of quiet wonder helps you rest, I'd be grateful if you tap like or subscribe. No pressure at all. Tell me where you're listening from tonight and what time it is there. Now dim the lights, maybe turn on a fan for a soft background hum, and let's ease into tonight's journey together. Somewhere between Mars and the great slow pull of the sun, a visitor drifts at 137,000 miles per hour. It's moving too fast to belong here, too silent to raise alarms, and yet every observatory on Earth is watching it. An interstellar traveller called 3i Atlas, the third confirmed wanderer from beyond our solar system. It will pass within 29 million kilometres of Mars, close enough for our spacecraft to feel its quiet presence, but far enough that no collision will ever come. Still, its arrival has stirred a restless fascination across the astronomical world, not for its speed or its path, but for the strange whispers in its chemistry, the way it behaves, the way it gleams, the way it refuses to act like anything we've seen before. Mars itself circles the Sun every 687 days, a cold red world with a thin carbon dioxide sky, frozen dunes, and dust devils that dance in the silence. When this visitor crosses its orbital plane, we'll see a moment of alignment that feels almost ritual. One world of rock, one traveller of ice and gas meeting under the steady gaze of sunlight. Astronomers calculate orbits with exquisite precision. They measure how gravity alone can twist a path into an elegant arc, how even the faintest tug from Jupiter or the solar wind can alter the motion of a grain of dust. But when they trace the route of 3i Atlas, they find themselves frowning at numbers that don't quite behave. Its speed, its mass, the angle at which it slices through the solar plane, all combine into a melody slightly out of tune with the usual cosmic orchestra. We've had other visitors before. In 2017, an elongated shard called Oumuamua swept through, tumbling end over end like a forgotten tool. In 2019 came Borisov, a true comet that flared and faded naturally. Each taught us something new about the architecture of distant systems, but this one, this third, seems different. Its trajectory is smooth, deliberate, almost polished. The orbit is hyperbolic, meaning it will never return once it departs. Yet in this fleeting moment, as it brushes past Mars, it offers us a window into the unknown. At 137,000 miles per hour, we can barely imagine the silence of its flight. In that vacuum, there's no roar, no wake, only the soft hiss of sublimating gases as they escape from the surface. Every molecule carries a story of formation long ago, perhaps in a cloud surrounding another star, perhaps in the cold womb of a galactic filament where elements first learned to bond. Even light itself moves slower through our instruments. Photons that left the sun 8 minutes ago now scatter off its icy surface and race back toward Earth, where they strike a mirror, a sensor, a human eye. Those photons carry the memory of their brief encounter, a spectral fingerprint that reveals the composition of the stranger. As the data arrives, scientists translate that light into graphs of brightness, into lines that reveal which atoms were stirred to glow. And within those lines, there are notes of unease, ratios that do not match, emissions that seem inverted, behaviours that imply more than chance. Some call it a puzzle, others call it noise, but everyone agrees. Something about this visitor asks to be understood. Mars will not notice, of course. Its thin air won't ripple, its dust won't tremble. The planet is accustomed to visitors far more violent: meteor strikes, dust storms, radiation bursts from the sun. But somewhere above its rust-coloured plains, our orbiters will turn their cameras outward, trying to capture a faint shimmer against the black. The high-rise instrument aboard the Mars Reconnaissance Orbiter, usually busy with sand dunes and crater walls, will pivot toward this fast-moving point, hoping to glimpse structure through the distance. We humans have always been drawn to approach. We reached across oceans, across decades, across the void between worlds. And now, from our little red outpost, we'll extend that gaze again, towards something that may have wandered for millions of years through interstellar darkness before arriving here. There is a kind of humility in realizing how unprepared we are. Every calculation of orbital mechanics, every estimate of mass or reflectivity comes wrapped in uncertainty. Space does not surrender its secrets easily. Sometimes, what seems like anomaly is merely misperception. Sometimes, misperception reveals a deeper pattern. For now, all we know is motion, the quiet geometry of an object older than our civilization, gliding through the gravity wells of our system. To witness it is to stand beside Mars in the grand silence and feel a brief tremor of perspective. The world turns, the orbit continues, and the comet, or whatever it truly is, keeps moving. If it were to whisper, it would speak in the language of reflected sunlight and frozen gas, a dialect we're only beginning to understand. So we wait, and we watch, and we listen in the wavelengths of the universe. Because once it passes Mars and fades toward the inner system, we might never see it again. But for a few nights, the cosmos offers us this alignment, a silent traveller and a red planet sharing the same thin sliver of space. A meeting written long before our species ever built telescopes, now unfolding quietly under the patient light of a star. It began, as so many cosmic mysteries do, with a number, 6 out of 10. That was the rating given by Harvard astrophysicist Avi Loeb when asked how confident he was that this interstellar object, 3I Atlas, might not be natural. 60%, he said. Not a declaration, not certainty, but a measured lean toward the unexpected. In science, even a fraction of confidence carries weight when the question is as immense as, are we alone? Loeb is no stranger to controversy. Years earlier, he suggested that Oumuamua, the first known interstellar object, might be artificial, a hypothesis met with both fascination and resistance. His reasoning then was rooted in anomalies, its shape, its non-gravitational motion, its lack of a tail. Now with 3I Atlas, the pattern returns, though the evidence this time comes not from imagination but from hard data. We might picture him late at night, surrounded by spectral charts glowing on a computer screen, quiet hums of instruments feeding in fresh numbers from telescopes across the world. Each reading carries a whisper of this traveller's nature, chemical ratios, emission lines, faint variations in brightness. To most astronomers, the story seems clear enough. A strange comet, perhaps unusually dry but still bound by natural physics. To Loeb, the ratios tilt the scale differently. Something about this visitor feels designed, or at least guided. Still, 6 out of 10 is not a verdict. It's an open door. It means perhaps. It means look closer. In astrophysics, confidence levels are often expressed in sigma values or probabilities, but rarely are they so openly human. 60%, a number just high enough to stir wonder, yet low enough to keep skepticism intact. Behind that number lies a process of deduction. The light collected from 3I Atlas by observatories like Hubble, the James Webb Space Telescope and the Very Large Telescope in Chile all agree on one unsettling thing. The object's chemistry is unlike any comet ever recorded. The gases it releases are almost pure carbon dioxide with only a trace of water. In ordinary comets, water dominates. Here, it's a mere whisper. Science thrives on anomalies. When patterns break, knowledge expands. Sometimes the explanation is mundane, a calibration issue, a reflection, an error in software. But occasionally a broken pattern points to a new law of nature, something no one had thought to look for before. Loeb's 6 out of 10 lives in that in-between space, between mystery and proof, between wonder and caution. To his critics, it's reckless to quantify uncertainty in such a way. To his supporters, it's refreshingly transparent. After all, most astronomical discoveries begin as unlikely suspicions. Pulsars were once thought to be alien beacons. Quasars seemed impossible until we learned to accept supermassive black holes. If we zoom out for a moment, we can see how fragile certainty is in astronomy. Light travels across millions of kilometers to reach us, filtered by cosmic dust, bent by gravity, and diffused by distance. We reconstruct entire worlds from a handful of photons. The deeper the data, the greater the humility it demands. And yet, something about 3i Atlas has drawn out more than analysis. It has awakened intuition, that ancient companion to reason. Loeb's rating isn't just about evidence, it's about the shape of the puzzle itself. A comet that emits pure nickel without iron. A trajectory that hugs the ecliptic like a thread laid by hand. A mass so immense it defies the expected distribution of interstellar wanderers. None of these, alone, prove technology, but together they invite the question. Across the scientific community, conversations unfold quietly. What does technological even mean when applied to something between the stars? Could an object shaped by processes we don't yet understand appear artificial without intention? Astrophysicists debate these nuances in late-night conferences, in data calls that cross time zones, their language calm and precise even when their imaginations stir. The beauty of science lies in that balance, the ability to wonder without declaring, to measure without believing. A 6 out of 10, after all, is a mirror for the human mind, part faith, part doubt, both necessary for discovery. In the broader story of astronomy, probabilities like this are rare but essential. When the cosmic microwave background was first detected, scientists estimated a similar confidence that it represented the afterglow of the Big Bang. Over time, evidence accumulated until doubt became history. Perhaps centuries from now, 3i Atlas will find its place in a similar timeline, either as the first misunderstood sign of intelligence or as a lesson in the vast creativity of nature. The universe loves symmetry, but it also loves exceptions. The spiral arms of galaxies follow predictable laws, yet each galaxy curls in its own quiet variation. The planets orbit in neat ellipses, yet one tilt or wobble can reshape climates and destinies. In that same way, every new interstellar visitor is a reminder that the cosmos is not finished teaching us what is possible. So we drift with Loeb's number, 60% chance of the unexpected, and let it rest gently in the imagination. It's not proof, but an invitation. Maybe 3 Atlas is just an ancient comet, hardened by eons of cold. Maybe it's something older, a relic from before the sun ignited, carrying chemistry from forgotten stars. Or maybe, as Loeb hints, it's something made, not by us, but by minds who once wondered, as we do now, whether they were alone. The truth will arrive slowly, in the careful cadence of observation and time. Until then, the number remains suspended like a tiny star in the dark, a small glowing measure of curiosity guiding us deeper into the night. When light from 3i Atlas first reached the James Webb Space Telescope, it arrived as a whisper in the infrared. Tiny oscillations of warmth spread thin across the void. Inside that signal was a surprise. The object's breath was made almost entirely of carbon dioxide. 95% CO2, just 5% water. That ratio is like hearing a familiar melody played in reverse. Comets in our solar system sing with water. Ice boils away, vapour drifts, tails glow blue in the ultraviolet. But this one is nearly dry, exhaling frozen carbon instead of the water vapour we expect. Astronomers leaned closer to their monitors, tracing the curves of emission lines that define a comet's character. Each line corresponds to a vibration of molecules, one for CO2, one for H2O, one for carbon monoxide. In this case, the water signal was faint, almost reluctant. The carbon dioxide line, however, blazed confidently. If comets are archives of their birthplace, then this was the signature of a world that formed in deep cold, far beyond the frost lines of any ordinary planetary system. The frost line, sometimes called the snow line, marks the distance from a star where volatile compounds can freeze solid. In our own system, it lies between Mars and Jupiter. Beyond that boundary, water becomes ice and can gather into comets. But for carbon dioxide to dominate, temperatures must be even lower, perhaps 10 or 20 times farther from a parent sun. It means 3I Atlas may have formed in a region so frigid that water could not condense at all, where only CO2 and methane could bind to dust. In the quiet chambers of data analysis, scientists began to consider what kind of star might host such conditions. Maybe a dim red dwarf, shining weakly across an extended debris field, or a star in a dense molecular cloud, where light can barely escape and temperatures fall close to absolute zero. The possibilities multiply, each one more intriguing than the last, and yet, even those explanations feel incomplete. The extreme ratio, 16 times more carbon dioxide than expected, defies the natural gradient observed across thousands of known comets. If it were simply a matter of formation distance, we would have seen others like it, but we have not. That's why, amid the data, a quiet unease spreads. It's as if 3I Atlas has been shaped by a chemistry we do not yet understand. The James Webb Telescope, with its mirror stretched like a golden sail, was built for such mysteries. Its instruments, NIRSPEC, NIRCam, MIRI, can isolate the faintest trace of a molecule billions of kilometers away. One of Webb's engineers once described its sensors as the eyes of patience, designed to stare unblinking into the ancient cold. When it looked upon 3 Atlas, those patient eyes recorded an object that simply did not behave. To make sense of the CO2 dominance, researchers built models of how sunlight interacts with ices. Normally, as a comet nears a star, the heat penetrates a few centimeters below the surface, freeing water first because it sublimates at lower temperatures. Carbon dioxide comes later, when the ice crust has already been thinned. But in this case, the pattern is reversed. CO2 erupts early and violently, as though the object's outer layers are made almost entirely of dry ice, with little else beneath. Some have suggested this might be an effect of cosmic aging. Over billions of years, water ice can sublimate slowly even in interstellar space, leaving behind carbon dioxide and complex organics. The result would be a desiccated core coated in dark residue, a comet stripped of its youth. But for that to happen, the object must have wandered for eons through the galactic dark, surviving the radiation and impacts that destroy lesser bodies. If true, 3I Atlas might be among the oldest travellers we've ever seen, a frozen memory from before our sun existed. Others think the chemistry might point to something more deliberate, though they speak softly about it. Industrial processes can separate volatiles in similar ways, refining one substance over another. It's a stretch, perhaps, but in a universe 13 billion years old, imagination can sometimes be a necessary tool. For now, the safest explanation remains the simplest. An interstellar relic forged in the coldest possible nursery, now thawing under the gentle furnace of our sun. Yet the mind drifts, as minds do, toward what-ifs. On Earth, carbon dioxide ice is known as dry ice. It sublimates at -78 degrees Celsius, forming fog that rolls across the floor of science demonstrations and stage performances. Imagine, then, an entire mountain of such material drifting through space. When sunlight strikes its face, it erupts in silent vapour, a ghostly fountain of gas expanding in all directions. Each molecule carries a small push, a faint exhalation that nudges the comet's path. In laboratories, physicists simulate these processes with cryogenic chambers and vacuum pumps. They watch grains of dust lift and dance as CO2 escapes beneath them. The same dance, magnified 1,000,000-fold, now unfolds somewhere near the orbit of Mars. Astrophysicists still debate whether these unusual ratios indicate an origin outside any known planetary system, or simply a long, slow evolution under interstellar conditions. the answer may never be singular. In the end, 3i Atlas could be both, a natural fragment altered by time until it seems alien to us. When we look at its spectrum, we're really looking backward in time. Each photon that Webb collected had been travelling for a few minutes from the Sun, but its story began much earlier, in the ancient chemistry of a star-forming cloud. Inside that cloud, carbon joined with oxygen under pressures we can only imagine. Billions of years later, that same bond glows in our detectors. Perhaps this is the true poetry of astronomy. Even when an object defies expectation, it still reminds us how connected we are to the cosmos. The carbon in our breath once burned in stellar cores. The oxygen in our lungs once drifted between galaxies. To study 3i Atlas is to study the inheritance of existence itself, the quiet continuation of cosmic chemistry. As we continue watching, the carbon dioxide continues to pour out, building a translucent veil around the nucleus. From far away it looks serene, but within that plume, physics plays out at frantic scales. Molecules racing at hundreds of meters per second, grains of dust spiraling outward, light scattering in all directions. And through it all, the mystery deepens, a comet that breathes differently, a voice unlike any other. When the Very Large Telescope in Chile turned its gaze toward 3i Atlas, the night air was still and thin. The desert around Cerro Paranal has seen countless stars, but not many secrets like this. In the long exposures taken from that summit, a peculiar signature appeared in the spectrum, a gleam of pure nickel and none of its usual companion, iron. Nickel and iron are cosmic twins. They are born together inside dying stars, fused in the final throes of supernovae. When a star collapses, its inner furnace binds lighter elements into heavier ones, and nickel and iron are inseparable in that creation. Everywhere we look, in meteorites, in asteroids, in the core of our own planet, they appear side by side, always in near equal proportion. To find one without the other would be like hearing thunder without lightning, an echo missing its source. And yet that's what the telescope revealed. Nickel shining clean and solitary in the spectrum traced through the glow of the object's escaping gases. The absence of iron lines was so complete it drew silence across the observatory room. Technicians rechecked calibrations, cleaned filters, and ran the analysis again. Still the same pattern. Nickel strong, iron invisible. Spectroscopy is a kind of language. Each element speaks in light, carving its own narrow bands into the electromagnetic spectrum. Astronomers learn to read those bands the way musicians read sheet music, recognizing a note by its position and brightness. Nickel sings in the near-ultraviolet and visible, with a faint hum in the infrared. Iron, usually close behind, leaves dozens of overlapping traces, but in this case the iron was mute. That muteness is difficult to explain. One possibility is temperature. Perhaps the object's outer layers are just cool enough for iron to remain locked in solid grains, while nickel, more volatile, escapes as gas. Another possibility is selective chemistry. Complex compounds like nickel carbonyl that break apart more easily than their iron-based cousins. These molecules could, in theory, release nickel atoms while keeping iron trapped. The problem is that no one has ever seen such behaviour in nature on this scale. A more daring thought, one that makes scientists uncomfortable, is that this pattern resembles something we create ourselves. In certain manufacturing processes, humans refine nickel to high purity, separating it from iron through chemical or thermal treatment. The resulting signature, nickel without iron, is a hallmark of industry, not geology. When Loeb mentioned this in an interview, he called it an observation, not a conclusion. Yet even a suggestion carries a kind of gravity. If this composition were to occur naturally, it would mean there are environments we haven't yet encountered, places where metallic elements separate in ways unknown to our physics. Perhaps deep in the cold interstellar medium, under the gentle bombardment of cosmic rays, strange reactions could favour nickel over iron. Perhaps the balance that holds across the universe has rare exceptions. Still, that idea, though comforting, remains speculative. To imagine the process in motion, picture sunlight glancing across the surface of the object, heating patches of exposed metal embedded in ice. As the temperature climbs, atoms begin to shake free, leaping into the vacuum. Each nickel atom catches sunlight for the briefest instant, scattering photons toward our telescopes. The distance is immense, hundreds of millions of kilometers, but the signal is unmistakable. The Very Large Telescope, or VLT, is actually 4 telescopes working together, their mirrors measuring 8 meters across. Through adaptive optics, they can correct for the trembling of the atmosphere, sharpening their vision to a near-perfect point. It's from such precision that this anomaly arises, not rumour or imagination, but carefully measured light, repeated and verified. A quiet debate has begun among spectroscopists. Some argue the iron may simply be there, hidden below detection limits, its emission lines blurred by dust or scattered light. Others suggest the nickel could come from a transient event, perhaps a pocket of vaporized material from a recent collision. Astrophysicists still debate whether such a process could produce the strength of signal observed, or whether it would fade too quickly to match the weeks-long increase seen across multiple observations. That increase is another puzzle. Between July and August, the nickel emission rose by a factor of 25. It did not merely appear and vanish. It grew, following the object's approach to the Sun. Something was changing on the surface, some reaction or release that accelerated with heat. Ordinary comets exhibit gradual patterns as ice sublimates, but here the curve steepened unnaturally fast. If we strip away the mystery, what remains is a rhythm. As sunlight intensifies, the surface yields more metal, and as the metal escapes, the spectrum brightens. That rhythm implies a form of feedback, a balance between energy and matter. But the composition, the purity of nickel, still refuses to fit. Elsewhere in the solar system, nickel plays a quiet role. It forms the hard cores of planets, hides in meteorites, and strengthens the magnetic fields of iron-rich worlds. It is both common and unassuming, a workhorse element. Yet here, it glows alone in space, detached from its usual partner, floating through a plume of carbon dioxide gas. There's a humility in recognizing how fragile our expectations are. For centuries, astronomy has leaned on the principle that physics is universal, that atoms behave the same way everywhere. 3i Atlas tests that principle, or at least teases it. Maybe, somewhere in the interstellar dark, chemistry finds a new equilibrium. Maybe we're seeing the fingerprints of an environment colder or older than anything our laboratories can recreate. Still, the idea lingers, quiet but persistent. If someone, somewhere, once shaped metal in space, if they built or mined or harvested on a scale vast enough to send debris drifting through the galaxy, then such an object might look exactly like this. Bright with nickel, silent in iron, breathing out the residue of intention. No one is claiming that's what we're seeing. But as the night turns over chilly and the telescopes wait for the next clear sky, the data from this single observation continues to hum in the background of scientific thought, a riddle written in starlight, waiting for the next line of translation. The story of 3i Atlas became even stranger when astronomers compared its brightness across time. In early July, its metallic emissions were faint, a barely perceptible shimmer of nickel atoms flowing outward from the surface. By late August, that shimmer had intensified 25 times over. The change was not linear, it was abrupt, almost impatient. Something within this object seemed to awaken as it neared the warmth of the sun. We've seen comets grow more active before. As sunlight strikes their icy crusts, sublimation releases plumes of gas that expand into vast halos of vapour and dust. The closer they move toward the sun, the more vigorous the outgassing becomes, following predictable laws of thermodynamics. But 3 Atlas does not follow those laws neatly. Its nickel emissions rise faster than any model can explain. Nickel is a heavy element, far less volatile than the usual gases of comets. For it to sublimate, surface temperatures must reach hundreds of degrees, far higher than what most cometary materials experience at this distance from the sun. And yet, there it is, nickel atoms glowing in spectral lines, accelerated by invisible energy, each one a small beacon in the darkness. In the laboratories of Earth, similar emissions are seen only in controlled environments, industrial furnaces, electrochemical separation, metallurgical processing. Of course, no one suggests a foundry exists within this traveller. Still, the pattern echoes that of processes we understand only through deliberate design. Perhaps some say 3I Atlas carries internal reservoirs of trapped gases that heat unevenly, cracking through metallic veins beneath the crust. When pressure builds, they burst outward, ejecting metal-rich vapour. Others wonder if the surface is coated in fine nickel dust, left behind by billions of years of slow erosion, each grain ready to leap into space once sunlight touches it. The explanations multiply, none entirely satisfying. We know this much. The emission rate doubles every few days as the object nears the sun. At times, it almost mimics the exponential curve of a chemical reaction rather than a natural sublimation process. The closer it comes, the brighter the nickel signature becomes, as though some hidden mechanism were regulating its release. In every new dataset, astronomers look for corroboration. The Very Large Telescope sees the same rise. The Webb telescope notes the same trend in infrared. Even smaller instruments detect the growing metallic line. The consistency is eerie. No noise, no fluctuations, just a steady crescendo of light. It's easy to forget, amid the numbers, that these events happen in silence. Out there, near the orbit of Mars, there is no sound, only vacuum and sunlight. The atoms escaping from the object's surface form invisible streams that curl and twist under solar radiation. Each nickel atom moves at tens of kilometers per second, yet from afar it appears motionless, suspended in a plume that catches the faint gleam of starlight. We sometimes imagine space as empty, but it is a sea of particles, charged and drifting, shaped by the wind from the sun. When that solar wind encounters an outgassing object, it creates ripples of magnetic pressure. Instruments aboard distant spacecraft can sense these ripples, tiny fluctuations in plasma density, echoes of unseen events. As 3 Atlas sheds its metallic breath, those ripples travel outward, crossing the invisible boundary between Mars and interplanetary space. At the European Space Agency's Operations Centre, engineers calculate when Mars orbiters might detect the passing wake. The High-Resolution Imaging Science Experiment, or HiRISE, aboard the Mars Reconnaissance Orbiter, can observe details as fine as a metre across on the Martian surface. Yet when aimed at this interstellar traveller, even that powerful camera will see little more than a glimmer, 30 kilometers per pixel. That is the scale of our distance. Still, within that glimmer lies everything we need to question our models. If the metallic emissions continue to rise, astronomers expect the object's brightness to shift from red to green, a transformation already hinted at in amateur images. Nickel and related compounds often radiate faint green hues when excited by sunlight. It's a quiet colour, the shade of oxidized copper, the same tone that crowns old statues on Earth. Seeing such light shimmer across a comet's coma is unprecedented. Perhaps the nickel sits close to the surface, exposed like ore veins on an ancient cliff. When sunlight warms those patches, electrons jump between energy levels, emitting photons of specific wavelengths, the spectral fingerprint we now record. If so, then the object's skin might be a mosaic of metals, each reacting differently as it rotates. Rotation itself adds another layer of intrigue. Measurements of periodic brightness. Fluctuation suggests a day roughly 16 hours long. As it spins, 3i Atlas alternately presents different hemispheres to the Sun. The increase in nickel could thus be a result of more reflective terrain turning into view, or it could hint at a deeper process, a progressive awakening of material as each side heats in sequence. The longer we observe, the more the line between physical and poetic blurs. A lifeless object cannot truly awaken, yet the data evokes that feeling. Every curve and flare suggests motion, reaction, intention. Even seasoned astronomers find themselves speaking in human terms, describing behavior, response, pulse. Language strains to remain objective when the cosmos performs something so unlike itself. In classrooms and planetariums, educators try to explain what such an anomaly means. They speak of spectra, of nickel's electronic transitions, of the energy required to separate metal from rock. Yet beneath the formal tone lies wonder, an unspoken thrill that we may be witnessing a new category of object entirely. Astrophysicists still debate whether this emission growth points to internal heating, surface chemistry, or something entirely new. The models remain incomplete, the simulations unsatisfying. But even uncertainty can be beautiful when it reminds us that the universe still holds uncharted territory. As the sun's light grows stronger, so too does the object's metallic glow. In a few weeks, it will slip behind the sun from our vantage point, unseen for months. By then, the nickel may surge again, or it may fall silent. Whatever happens, those measurements will remain in our archives, a testament to the quiet power of observation. It's easy to imagine, in the deep calm of night, that 3i Atlas breathes in light and exhales metal, like a frozen lung rediscovering warmth. In truth, it's only physics at work, simple interactions of energy and matter. Yet when those interactions produce something the laws can't quite explain, we feel the old pulse of wonder again. Perhaps that is the true gift of this traveller. Not the data alone, but the feeling that after centuries of watching the sky, the cosmos can still surprise us. When the first photographs taken by amateur astronomers began to circulate, they looked ordinary at a glance, faint smudges of green against the black sea of space. Yet, when those images were brightened, sharpened, and compared side by side, something unexpected emerged. Beneath the soft glow of gas there appeared structure, lines, edges, and geometry where none should be. It started with a pair of dedicated observers using modest backyard telescopes under pristine Namibian skies. Their names slipped quietly into astronomy forums, not university journals. They had captured 3i Atlas during a lunar eclipse, using standard tracking mounts and stacking software to blend dozens of exposures. The result was subtle, but startling. A glow that was not diffuse, not cloud-like, but shaped, almost solid, with faint symmetry across its axis. Soon, the images spread through communities of skywatchers. Some saw hexagonal hints, others a spindle of light like a seed pod. Most dismissed it as artifact, a product of imperfect tracking or atmospheric turbulence. The amateur sky, after all, is full of illusions. A wisp of cloud, a dust mote, a misaligned pixel can conjure miracles that vanish under scrutiny. And yet, these shapes persisted across different nights, different instruments, even different continents. Professional astronomers, cautious by training, were quick to respond. They spoke of motion blur, chromatic aberration, stacking errors, all plausible, all likely. But their caution carried a familiar tone, the voice of science guarding its gates. For every image that challenged the model, a dozen replies urged restraint. Still, the curiosity could not be extinguished. If even a fraction of those structures were real, the implications were enormous. The tension between amateurs and professionals is older than photography itself. Some of our greatest discoveries, comets, novae, even the rings of Saturn, were first glimpsed by passionate observers far from institutions. The sky, after all, belongs to everyone. It doesn't ask for credentials when you look up. In those weeks, online astronomy boards filled with side-by-side comparisons. Some posted Hubble's official images showing a smooth teardrop halo. Others uploaded their own backyard frames, grainy but insistent, showing shapes hidden beneath the haze. The debates were fierce but strangely polite, like murmured arguments in a library. One side appealed to optics, the other to pattern recognition. In truth, both were driven by wonder. A telescope is a translator. It turns light into comprehension, but only if we listen carefully. Every optical system, from a backyard mirror to a space observatory, leaves fingerprints on what it sees. To discern reality from artifact, astronomers study the point spread function, the way a perfect point of light should appear when blurred by atmosphere and instrument. Deviations from that pattern can signal either error or discovery. In this case, the deviations were real. The question was why. Some amateurs used filters to isolate wavelengths. In green and blue light, the object appeared compact, concentrated. In red, it diffused like a cloud. That's typical of gas, yet the green channel revealed sharpness that gas alone cannot produce. Could it be a denser core or a reflective surface hiding within the coma? A few images taken during still nights, when the air above the telescope was steady, seemed to show parallel streaks, faint but measurable. Those streaks might be trails from expelled particles, or they might be alignment artifacts from the stacking process. When asked to replicate the results, larger observatories declined. Their schedules were packed, their instruments were tuned for other priorities. The sky's calendar is always full, and time on big telescopes is precious. Meanwhile, online, the human imagination bloomed. Some saw in the geometry the outline of machinery, others the petals of a crystalline shell. Skeptics reminded them that seeing structure in chaos is one of our oldest habits. The brain, like a lens, wants to focus on meaning. A spiral in the clouds, a face on Mars, a shimmer in the stars. We build stories from patterns even when the universe offers none. Still, one cannot dismiss curiosity entirely. What if the geometry hinted at internal layering, like onion skin strata from eons of sublimation and refreezing? Comets evolve as they travel. They shed and rebuild, leaving crusts of metal-rich dust and voids of trapped ice. Those layers can refract light into odd shapes. A natural cause remains not only possible but likely. And yet, the allure of the alternative persists, a quieter question hidden behind the scientific one. What if we are glimpsing design where we expect only randomness? Such questions echo through the history of exploration. When the first deep-sea probes filmed strange ridges on the ocean floor, some claimed ancient architecture. Later, geology proved them natural. When Mars revealed rectangular mesas, the face filled headlines before being explained by shadows. Discovery is often a conversation between illusion and truth, and only time decides who wins. In one of the more poetic discussions online, a commenter wrote, "Maybe what we're seeing is what it wants us to see." Others laughed, yet there was beauty in the thought. In deep space, perception is already a negotiation, between signal and noise, between light and the limits of our instruments. Professional astronomers eventually released updated statements. They acknowledged the amateurs' enthusiasm and the importance of independent observation, but reaffirmed that nothing beyond natural phenomena had been confirmed. For now, the structures remained unverified optical effects, but their caution could not undo the fascination spreading through the stargazing community. It is often amateurs who stay awake long after observatories close, pointing small mirrors skyward, capturing light that falls freely to anyone patient enough to gather it. And in those long hours, beneath cold skies, the boundary between data and dream thins. Whether the shapes beneath Three Eye Atlas's veil are real or imagined, they have already done something extraordinary. They have reminded thousands of people that the sky is still alive with mystery. Somewhere tonight, a telescope hums quietly on a balcony, tracking a faint green point as it moves against the background stars. The images it gathers will join the conversation, one more small thread in the tapestry of collective observation. In a way, that's how discovery truly works, not in isolation but in chorus. So we keep looking, together. Each photon caught in a backyard mirror adds to the larger understanding. And maybe, when the data from the great telescopes finally returns, it will find that what amateurs glimpsed through the shimmer of atmosphere was not illusion after all, but the first faint outline of something we have yet to name. On a clear July night, the Hubble Space Telescope captured a view that made astronomers fall silent. Floating within the black canvas of deep space was a faint teardrop-shaped glow, Three Eye Atlas, wrapped in its dusty halo. But something about the image felt off, even unsettling. The bright region wasn't streaming away from the sun, as every comet should. It was pointing toward it. For centuries, comet tails have obeyed a simple rule. Sunlight and the solar wind push gas and dust outward, forming a luminous plume that always trails behind. The physics is straightforward. Photons exert pressure, and charged particles flow from the sun like a constant breeze. The result is a tail that faithfully points away from that fiery centre, no matter which direction the comet travels. But here, in this Hubble frame, the glow stretched forward. Toward the light, it was as if the comet were resisting the sun rather than retreating from it. The discovery came during routine image processing. Scientists at the Space Telescope Science Institute double-checked everything: the orientation, the tracking rate, the background subtraction. Could Hubble's motion have caused a false elongation? Could the image have been flipped? No. Every verification yielded the same conclusion. The bright plume extended sunward. They called it an anti-tail, though even that term barely fit. True anti-tails exist. They appear in some comets when perspective tricks our eyes, making the tail seem to point forward. But such illusions depend on viewing geometry, when Earth, comet, and sun align just so. In this case, the geometry didn't match. The forward glow was real. Imagine it, a tear of light. Glowing softly in defiance of physics, moving through the vacuum at tens of kilometers per second. The light curves gently, as though drawn by invisible threads. Inside that glow, dust particles shimmer, each one a tiny mirror scattering sunlight in strange directions. One theory suggested that Three Eye Atlas was shedding ultra-fine dust, so small that solar radiation pressure dominated its motion. These particles could have been pushed ahead of the nucleus by electromagnetic forces rather than swept behind by gravity. Another idea invoked electric charge. Sunlight ionizes the dust, and in the sun's magnetic field, those charged particles could trace curved, looping arcs. If that were true, Three Eye Atlas might be wrapped in a faint electric cocoon, interacting with space in ways that normal comets do not. Still, there were skeptics. Some proposed that the bright region might not be a tail at all, but a jet, a focused spray of material venting from the surface like a geyser angled toward the sun. Comets often exhibit localized jets, driven by pockets of gas bursting through their crusts. If the vent happened to face forward, that might explain the image. Yet no known comet jet has ever produced such clean geometry. Hubble's moving target tracking, normally precise to fractions of an arcsecond, added to the complexity. The telescope must continuously adjust its aim to follow fast-moving objects, compensating for their shifting position across the sky. Any error, even slight, can elongate images, but the stars in the background appeared as faint streaks, while the object itself remained perfectly sharp. That meant the tracking was working. The forward glow was not an illusion of motion, it was part of the comet itself. When the image was released, astronomers debated quietly. Most agreed it was worth further observation, but time on Hubble is precious, and the schedule was full. The James Webb Space Telescope had also observed the object earlier in infrared, but its longer wavelengths couldn't resolve the same structure. For the moment, the anti-tail remained a snapshot, a single frame of inexplicable beauty. To the casual observer, it's just light, but to scientists, it's a riddle written in geometry. Light tells us how matter moves, and matter tells us what forces act upon it. If dust moves toward the sun, then some unseen process is reversing the rules. Perhaps the particles are being magnetically funneled. Perhaps their composition, rich in nickel, poor in iron, gives them unusual reflective or magnetic properties. Astrophysicists still debate whether metallic grains could respond differently to the solar wind, bending their path inward instead of outward. In the months that followed, other telescopes aimed their mirrors at 3i Atlas. The Gemini South Observatory caught it in late August and found that the bright forward glow had faded. In its place stretched a more familiar tail, streaming gently away from the sun. Between July and August, something had changed. Either our perspective shifted, revealing what had always been there, or the comet itself had evolved. Perhaps as it approached the sun, new jets opened, or the fine forward dust dispersed, leaving behind coarser grains that obeyed ordinary radiation pressure. Astronomy often works in such before and after glimpses. One image reveals a mystery, the next brings relief, and the truth lies somewhere between. But even if the anti-tail was fleeting, it told us that this object's behaviour was far from normal. It hinted at complexity, a dynamic interaction with light, dust and magnetism that we still struggle to model. There's a lesson here about humility. We like to think the laws of physics are complete, that we can predict every dance of matter and energy. Yet the cosmos keeps offering subtle exceptions, moments when the universe reminds us that our understanding is still young. In the soft light of those Hubble pixels, humanity witnessed a paradox, a comet that pointed its luminous breath toward the very star that was unmaking it. It's easy to imagine, in that gesture, something almost symbolic, an ancient traveller facing the light of a younger sun, offering up its final fragments before fading away. Astronomers will analyse that image for years to come, comparing it with simulations, searching for overlooked forces. Maybe the answer lies in grain-size distributions, maybe it lies in the object's spin, or maybe, as Loeb has mused more than once, the answer lies in an intention we are not yet equipped to recognise. For now, we only know what we saw, a forward-facing glow in defiance of every rule, captured by a telescope orbiting 400 miles above a small blue world. Sometimes that is enough. The rest, like the dust itself, will settle slowly, drifting toward understanding with the patience of light. By the end of August, the strange forward glow had disappeared. In its place stretched a more familiar sight, a delicate tail sweeping away from the sun, pale and narrow, like smoke carried by an unseen breeze. Gemini South, the great telescope in Chile, captured the new image under still air and cold stars. The anti-tail of July had become a textbook cometary plume, trailing behind 3i Atlas in perfect obedience to solar physics. At first, this shift seemed like reassurance, a return to normality. Yet beneath that relief lingered another question. What changed? Between Hubble's image on July 23rd and Gemini's on August 27th, only 5 weeks had passed. The object had moved closer to the sun, yes, but not enough to fully reinvent its structure. Some researchers pointed to geometry, as both Earth and the comet continued their orbital motion, a viewing angle shifted by millions of kilometers. What once appeared forward might now appear behind simply because of parallax. Others suggested an authentic transformation. The dust environment had evolved, the surface vents had awakened, and new material was escaping into sunlight replacing earlier patterns with more conventional behaviour. Whatever the cause, the new tail revealed details that had been hidden before. Through multiple filters, astronomers traced its composition: fine dust in blue light, gas emissions glowing green, and faint red echoes from larger, slower grains. In the near ultraviolet, the object appeared smaller and sharper, the signature of submicron dust pushed rapidly outward by solar radiation pressure. In longer wavelengths, the structure stretched farther and diffused, tracing the heavier grains too massive to accelerate quickly. These colour contrasts tell a quiet story. Each particle's size and density determine how sunlight moves it. Small grains, lighter than a snowflake, race ahead of the solar wind, forming thin, sweeping arcs. Larger grains drift lazily behind, defining the thicker body of the tail. By comparing their separation, astronomers can infer how much force the sun exerts on different scales of matter. It's a gentle dance of pressure and gravity, repeated by every comet that wanders through our star's domain. But in this case, the dance steps are unusual. The data shows velocities faster than models predict, dust accelerating at tens of meters per second more than expected. That implies either stronger outgassing or lower density material, both hints of instability within the nucleus. 3 Atlas may be less a solid rock than a porous snowball, held together by weak cohesion, vulnerable to collapse. If that's true, then each rotation could be reshaping its form, shedding layers into the void like ash blown from cooling embers. Gemini South's spectrograph added more clues. The gas within the tail contained cyanide radicals and carbon monoxide, familiar cometary chemicals but present in extraordinary quantities. Cyanide emissions in particular had risen sharply since July, paralleling the growth of nickel vapour detected earlier. That correlation intrigued researchers. Could the nickel and cyanide be linked through the same mechanism? Perhaps ultraviolet sunlight was breaking apart deeper compounds buried in the surface. Or perhaps something far stranger was happening, a coupling of metals and volatiles beyond our current models. When astronomers speak of uncertainty, it's not a sign of ignorance, but of precision. They measure how well their equations fit the observations, and 3i Atlas refuses to fit neatly anywhere. The August data forced revisions to existing comet codes, those algorithms that simulate dust motion, mass loss, and tail brightness. One by one, parameters were adjusted: outflow rate, rotation period, grain reflectivity. Each change brought the model closer, but none could reproduce all the features at once. Some mysteries remain immune to equations. Meanwhile, amateur observers continue to watch from Earth's darker corners. Their cameras caught the tail lengthening night after night, extending millions of kilometers into the black. From their perspective, the transformation looked almost alive. The red hue of July faded into jade, the coma brightened, and the tail, once short and sunward, now streamed like a banner behind the moving nucleus. To the eye, it looked as though 3i Atlas had turned its face toward the sun in greeting and was now gliding away, exhaling the last of its secrets. The mathematics of dust transport tells us that a tail's shape depends not only on sunlight but also on time. Each particle released follows its own orbit, curving outward along predictable arcs. Together, they form the illusion of a continuous streak. But what's visible tonight is made of dust released days, or even weeks earlier. So the August tail we see may carry memories of the July glow, a residual echo of the forward plume now drawn backward by time and motion. There's something quietly philosophical in that idea. The light we see always comes from the past, and the dust in every comet tail is the frozen past in motion. In studying through Atlas, we're not watching the present at all. We're seeing its history unfold moment by delayed moment. Even its brightest secrets are echoes. At Gemini South, a spectrograph technician described the observation as a whisper turning into a sigh. The phrase captured the feeling of transition, the object losing its defiance, settling into the familiar rhythm of cometary behaviour. But even in conformity, 3i Atlas remains different. Its gas ratios, its metallic plume, its unpredictable geometry, each trait keeps it at the edge of explanation. Astrophysicists still debate whether the new tail marks stability or prelude. Sometimes, comets that grow too active too quickly disintegrate near perihelion. Thermal stress fractures them, releasing torrents of dust before they vanish entirely. If that fate awaits 3i Atlas, the August images may be among the last glimpses of an intact nucleus, or if it truly is something more durable, it will survive the sun's heat and re-emerge stronger in December, still cloaked in its emerald glow, in the silence of observatories and the patient persistence of amateur watchers. A strange anticipation builds. For now, the data flows like soft static. Light turned to numbers, numbers turn to questions. Between July's paradoxical forward plume and August's obedient tail, the truth likely lies in some delicate middle ground, shaped by geometry, chemistry, and chance. Perhaps the cosmos is reminding us that transition itself is the natural state of all things. Dust becomes light, light becomes data, data becomes wonder, and through that wonder we glimpse again how little we truly know, and how beautiful that unknowing can be. Not long after Gemini South recorded the new tail, another instrument joined the search for answers. NASA's Sphere-X mission, an infrared survey telescope built to map the chemical fingerprints of the entire sky, turned its sensors toward 3i Atlas. Unlike the great optical observatories, Sphere-X does not seek shapes or colours. It listens for warmth, the faint glow of heat that every object emits even in the coldest dark. What Sphere-X saw was simple and strange. No extended halo, no dusty silhouette, just a single point of light. A bright dot where there should have been a fuzzy glow. Infrared telescopes are supposed to reveal more than visible light can. Dust that hides in optical wavelengths glows warmly in the infrared, tracing the structure of comas and tails that ordinary cameras cannot see. When comets pass close to the sun, their ices boil into vapour, and the surrounding dust radiates gently in infrared bands. But 3i Atlas offered none of that. It appeared compact, concentrated, a thermal point rather than an extended source. At first, some thought this might be an artifact of distance. Sphere-X is optimised for wide-field sky mapping, not fine detail. But even within its resolution, the data suggested something real. The heat signature was tightly confined, far more so than expected for a comet producing so much gas. This contradiction deepened the mystery. If the object was outgassing vigorously, the escaping material should absorb sunlight and re-emit it as diffuse infrared radiation. Yet Sphere-X recorded almost no such emission. Either the dust was unusually cold, the grains highly reflective, or the surface emitted little heat to begin with. All three possibilities break from the standard playbook of comet physics. The simplest explanation might lie in composition. Carbon dioxide, which dominates 3i Atlas's emissions, sublimates differently than water ice. When CO2 transitions from solid to gas, it carries away less heat, leaving the surface cooler than a typical comet. In that sense, the lack of infrared glow could reflect efficiency, an icy body shedding gas without warming much itself. Still, even that logic falters under scrutiny. The nickel emissions detected earlier require heat, energy, and vigorous vaporization. Something doesn't add up. Astronomers began to wonder if they were seeing two phenomena at once: a metallic surface shedding vapor, surrounded by a shell of highly reflective dust. Such dust could scatter sunlight while blocking heat from escaping, making the object appear bright in visible wavelengths yet dim in infrared. It would be like watching a lantern wrapped in a mirror, luminous to the eye, invisible to a thermal camera. There's precedent for reflective materials in space. Some asteroids covered in metal-rich regolith reflect far more light than their size would suggest. Others hide carbonaceous compounds that absorb light completely, making them darker than coal. 3I Atlas seems to oscillate between these extremes, too bright at times, too dim at others, depending on the wavelength. It behaves as if its surface were patchwork, alternating between mirror and shadow. In one of the mission's data briefings, an engineer described Spherex detection as a point where there should be a plume. The phrasing stuck. It became shorthand among astronomers for this object's many paradoxes. A point where there should be a plume, a whisper where there should be a roar, an order where there should be chaos. If the Spherex readings hold, they suggest that 3I Atlas's thermal inertia, the ability of its surface to retain heat, is extraordinarily low. That could mean the material is porous, like aerogel, riddled with voids that trap cold. Or it could mean a metallic crust that reflects sunlight before it can penetrate. Both options are fascinating, both feel improbable. Astrophysicists still debate whether the difference between Spherex and optical observations is purely instrumental or truly physical. It might be that the object's emissions fluctuate rapidly, growing and fading in the hours between observations. Or perhaps we're witnessing a property that challenges the boundary between comet and asteroid, an interstellar hybrid that defies classification. As the data filtered through research channels, one quiet thought surfaced repeatedly. Could the Spherex point source indicate something compact beneath the haze, something with structure, a nucleus less like a pile of rubble and more like a single coherent body? It would fit with the mass estimate suggesting a solid 5-kilometre object. But if that is true, how does such solidity coexist with its extreme outgassing? A comet so dense should be inert, and yet, here it is, alive with metallic breath. There's a soft irony in how our tools reveal the universe. Each telescope speaks a different dialect of light. Optical instruments capture the shimmering visible dance. Infrared hears the warmth of motion. Radio listens to vibration. No single instrument tells the whole story. Only by weaving them together do we begin to sense the truth. And with 3 Atlas, those threads refuse to align. For the scientists watching from control rooms, the contradiction was both frustration and wonder. One researcher described it as trying to solve a puzzle whose pieces change shape every night. Another compared it to listening to an orchestra where every instrument plays in a different key. Yet even dissonance can be beautiful when it points toward discovery. In the stillness of its orbit, the object gives nothing away. From our perspective, it is just a speck crossing the constellations. But within that speck lies a chemistry that defies expectation, a surface that mocks our models, a silence that contains more information than noise ever could. Perhaps that's why 3I Atlas captures our imagination so deeply. It's not just a comet or a curiosity. It's a reminder that the universe still keeps secrets. Even our finest machines can't yet decipher. The Spherex data remains under analysis, its meaning unsettled. Some say it's a calibration glitch, others call it a discovery. Either way, the object continues its path, reflecting light where none should be and hiding heat where all should shine. A paradox in motion, gliding past Mars and into history. And somewhere in that contradiction, in that point where there should be a plume, we sense the quiet persistence of the unknown still holding its breath among the stars. When astronomers finally mapped the full trajectory of 3I Atlas, the numbers carried their own quiet astonishment. The object was not tumbling randomly through the solar system. It was gliding in perfect alignment with the ecliptic, the flat plane where nearly every planet circles the sun. But it was moving in reverse, almost exactly opposite the direction of planetary motion. The inclination measured roughly 175 degrees. In the language of orbital mechanics, that is nearly perfect symmetry in opposition. If this were chance, it was an elegant one. The probability of an interstellar object entering our solar system at such a shallow angle, so precisely within the same plane as the planets, is roughly 1 in 500. Space is three-dimensional after all. Visitors from the galaxy could arrive from any direction, above, below, sideways through the sun's gravitational field. But this one chose the plane where the worlds lie, as if following the invisible chalk line that binds the orbits of Earth, Mars, and Jupiter. Statistical improbability alone does not make something artificial, yet the elegance of the geometry lingers in the mind. Our solar system is not a random scatter of orbits. It is a disk born from rotation and dust. Most interstellar travellers, ejected from their own stellar nurseries, should wander in at wild angles. To see one thread itself so precisely through our planetary stage feels almost deliberate. When orbital parameters were first plotted, the path resembled a long curve that slipped between Mars and the Sun before bending back toward deep space. But what caught researchers' attention were the near misses, close approaches to several planets along the way. On October 3rd, it would pass within 29 million kilometres of Mars. Months later, it would skirt Venus at less than 70 million kilometres, and in March of 2026, it would sweep past Jupiter, only 54 million kilometres from the giant's cloud tops. None of these encounters are dangerous, but together they form a curious chain, a tour through the inner solar system as though drawn to its major worlds. Astrodynamicists ran simulations backward in time, retracing the object's path through the stars. When followed far enough, the orbit led outward to the thick disk of the Milky Way, a population of ancient stars that orbit above and below the galactic plane. From there, 3I Atlas would have travelled for billions of years before reaching us, perhaps born from a planetary system long dead. It carries with it the history of a time when our sun had not yet ignited, a relic older than Earth itself. Yet the precision of its route through our system unsettled even those comfortable with coincidence. When Harvard's A.V. Loeb described the orbit as remarkably fine-tuned, his words rippled across conference halls and online discussions. Fine-tuned implies intention, but it can also mean nature's own precision, gravity's silent artistry. Either way, it reminded everyone that the difference between randomness and design often lies only in the interpretation of beauty. The mathematics of celestial motion are beautiful in their own right. Every orbit, whether circular, elliptical, or hyperbolic, can be described by 6 elements: semi-major axis, eccentricity, inclination, longitude of ascending node, argument of perihelion, and true anomaly. Together they define not just where an object is, but how it moves, its tilt, its stretch, its timing. For 3I Atlas, those numbers read like poetry: an inclination of 175 degrees, an eccentricity greater than 6, a perihelion inside the orbit of Venus. Each term adds to the picture of a visitor briefly intersecting our cosmic neighbourhood before returning to the dark. If we step back to imagine the scene in 3 dimensions, the geometry becomes almost cinematic. Picture the solar system as a thin disk of glowing dust. From far above, the orbits of the planets form delicate concentric rings. Then imagine a solitary traveller entering from below that disk, climbing upward through the plane, and exiting above it again, an arc of motion that intersects the paths of worlds without ever striking them. The trajectory is steep, precise, almost graceful. Some scientists argued that such alignment was not impossible at all, that our telescopes by nature are biased toward detecting interstellar objects that pass near the ecliptic. Those entering at steep angles are often missed, too faint and too fast for our instruments to track. The ones we notice, therefore, are those that happen to align with our observational sweet spot. Selection bias, they said, can make coincidence look intentional. Others were not so sure. Even allowing for detection bias, the odds remain slim. A 1 in 500 chance may sound small, but in a universe that tends toward chaos, small odds are sometimes the loudest whisper. Perhaps it is nothing more than a roll of cosmic dice. Perhaps, as Loeb mused, the odds themselves are the message. The orbits near coplanarity with the planets also means that sunlight will strike the object from angles similar to those we see reflected from familiar worlds. That makes it easier to observe spectrally but harder to distinguish background motion. For weeks at a time, 3I Atlas appears to move slowly against the star field, its apparent velocity deceptive. Only calculations reveal how swiftly it cuts across the solar system, 137,000 miles per hour, a streak of silence threading through the same plane that holds Earth. In that thin cosmic sheet, even small changes in trajectory can carry deep meaning. Astronomers track how non-gravitational forces, like outgassing jets or radiation pressure, alter a comet's motion. So far, 3 Atlas has shown almost none. Its path is clean, purely gravitational. That steadiness adds to the sense of intention, though physics alone can explain it. A massive object resists perturbation. Its sheer inertia smooths the chaos. Yet the human mind continues to wonder whether such steadiness is only a byproduct of mass or a sign of control. Astrophysicists still debate whether trajectories like this one hint at something deeper, a pattern among interstellar visitors, or merely coincidence amplified by attention. Perhaps as more are discovered, the statistics will flatten and the mystery will fade into normalcy. Or perhaps, in tracing their paths, we will find a subtle alignment repeated too often to ignore, a geometry that connects systems across light years. For now, 3 Atlas sweeps silently along the ecliptic, passing each planet like a quiet guest who somehow knows the layout of the house. Whether that knowledge is coincidence or design remains unanswered, but the elegance of its orbit, its mirrored path through the Sun's family, reminds us that even in mathematics there can be grace, and in grace, a whisper of wonder. The deeper astronomers studied the numbers, the heavier the implications became. By late September, after more than 4,000 precise observations from telescopes across the world, a new consensus began to form. 3 Atlas was enormous. The figures placed its mass at roughly 33 billion tons, its nucleus at least 5 kilometers wide, and its behavior stubbornly immune to the usual physics of comets. This weight changes everything. A comet of that scale should have revealed itself long before. Interstellar space is filled with smaller fragments, icy dust grains, shattered asteroids, and frozen snowballs born of distant planetary systems. If size distributions follow the same patterns we see in our own solar system, there should be hundreds of thousands of minor objects for every giant like this. Yet somehow, we found the giant first. That statistical puzzle carries the echo of improbability. The discovery of one massive visitor before a swarm of smaller ones defies the rules of cosmic sampling. It would be as though the first fish ever caught in an ocean were a blue whale. Astronomers, cautious as always, turned to models to test the odds. They simulated millions of random ejections from hypothetical planetary systems and watched where those fragments drifted through the galaxy. None matched the odds we've observed. Either 3I Atlas is a singular fluke, or we're seeing something non-random. Then there's the question of movement. When comets heat up and release gas, the escaping material acts like tiny rocket exhaust, nudging their orbits slightly. These accelerations, called non-gravitational forces, are easy to detect with modern instruments. Even a shift of a few meters per second is measurable across millions of kilometers. But in 3I Atlas, no such deviation appears. Its path is as smooth and precise as if drawn by geometry itself. To resist that kind of push, the object must be incredibly dense or tightly bound. The mass calculations confirmed it. 33 billion tons moving under gravity alone, unbothered by the jets of carbon dioxide erupting from its surface. That weight explains its steadiness, but raises another question. How could an interstellar fragment remain intact and massive across billions of years of collisions, radiation, and cosmic erosion? One possibility is that the object is not a fragile cluster of ices like most comets, but a consolidated monolith, perhaps metallic at its core. Such solidity would resist fragmentation and produce less acceleration from gas release. The earlier detection of pure nickel lines lends subtle support to this idea. If nickel exists on or beneath the surface, the crust could behave more like metal than dust. Astronomers compared it with the few other interstellar objects we've seen. Oumuamua, discovered in 2017, was no more than a few hundred meters long, thin and elongated, tumbling unpredictably. The second, Borisov, was smaller still. A faint ice-rich comet that behaved normally, and now 3 Atlas dwarfs them both, a massive traveller whose movements are pristine and whose chemistry refuses classification. In data plots, these 3 points form an odd triangle: tiny, smaller, massive. There should be a continuum between them, a spectrum of sizes bridging the gap, but the universe seems to have skipped steps. That absence nags at researchers. Either the smaller objects exist and remain unseen, or 3I Atlas was never part of the same random distribution to begin with. Some scientists quietly entertain the more radical possibility that it was launched, not ejected. An artificial body, built or guided, could have mass without instability and could follow a calculated course through planetary systems. The thought remains speculative, whispered rather than proclaimed, but its logic is internally consistent. A design trajectory would explain the precision, the lack of acceleration, even the improbable size. Still, extraordinary claims require extraordinary evidence, and so the speculation remains at the edge of polite discussion, a flicker of curiosity beneath the sober surface of research. Astrophysicists still debate whether the mass could be overestimated. Perhaps the brightness misleads us. Perhaps the nucleus is smaller but covered in unusually reflective material. That's possible, but infrared data from SphereX suggests otherwise. If the surface were purely reflective, it would emit more heat than observed. The thermal silence indicates genuine bulk. In the absence of contradictions, the simpler explanation, its staggering mass, stands. To hold together across eons, an interstellar object must survive forces that would grind lesser bodies to dust. Galactic radiation, micrometeorite impacts, and temperature extremes all conspire to erode fragile comets. The survival of 3I Atlas hints at density, resilience, and perhaps magnetic cohesion within. It could be a remnant core, stripped of its outer layers during past encounters, leaving behind only the heavy skeleton of a former world. Still, the idea that such an enormous object travelled unseen until now reminds us how limited our watchfulness truly is. The solar system, though vast, is only a tiny pocket of the galaxy. Our instruments scan narrow slices of sky, and many interstellar visitors likely slip through unnoticed. We catch only what chance allows us to glimpse. There's also a philosophical dimension to this discovery. When we speak of probability in astronomy, we often forget that the improbable still happens somewhere. In an infinite expanse, 1 in 500 events occur every day. The miracle is not that such coincidences exist, but that we happen to be here to notice them. And yet, when light from 3I Atlas reaches our detectors, it carries not only data but meaning. Its mass, its stability, its alignment, all conspire to whisper that the cosmos may be more intentional in its patterns than we dare admit. Perhaps it's nothing more than gravity sculpting perfection from chaos. Or perhaps, somewhere beyond our models, there is design embedded in motion itself. For now, the numbers stand like quiet monoliths. 33 billion tons, 5 kilometers wide, a trajectory unbent by anything but sunlight and gravity. It moves with the grace of inevitability, a mountain adrift among planets, following a course that feels both ancient and precise. We measure, we model, we compare, but sometimes the act of observation itself feels like reverence. Watching this object move through the sun's domain, steady as a heartbeat, we are reminded that mystery need not shout to be profound. It can drift, silent and massive, through the measured corridors of space, inviting us to wonder whether gravity alone is truly all that moves it. When the James Webb Space Telescope turned its golden mirrors toward 3I Atlas, the data it returned seemed at first like a simple confirmation of earlier reports. But hidden within those spectra was a revelation so strange that even seasoned comet researchers hesitated to trust it. The gas plume surrounding the object was not the familiar blend of water vapor and dust. Instead, it was almost entirely carbon dioxide, 95%, with only a trace 5% of water. That ratio is 16 times more extreme than any comet known within our solar system. Typical comets, drawn from the Kuiper belt or Oort cloud, are water-rich. They formed in regions cold enough to trap vast reserves of frozen H2O mixed with carbon-based ices. The carbon dioxide component is usually secondary, a thin veneer that sublimates easily as the comet nears the Sun. But here, the balance is reversed. This visitor is a dry ice body with only whispers of water, an inversion of everything we expect. The finding surprised even those who had predicted anomalies. At its observed distance from the Sun, water ice should dominate outgassing, because it vaporizes more readily under warmth. Yet the spectrograph showed the opposite. Torrents of carbon dioxide gas streaming into space, while water lines remained faint and hesitant. It was as though the comet were exhaling a different chemistry altogether, shaped by a world alien to our own. Carbon dioxide is abundant in the universe, but such purity suggests formation under extreme conditions, perhaps in the frigid outskirts of a distant stellar nursery, or within a molecular cloud colder than any region of our solar nebula. In those environments, water freezes out completely, while CO2 remains volatile enough to collect near the surface. The result is a body sculpted from frozen breath, not ice. Adding to the strangeness, Webb detected traces of carbon monoxide and carbonyl sulfide, gases that normally accompany deep space chemistry. Their ratios, combined with the overwhelming CO2 dominance, hint at an origin far beyond our local interstellar neighbourhood, perhaps in the thick disk of the Milky Way, where ancient stars forged planets under different metallicities and temperatures. Astrophysicists still debate whether such chemistry could survive billions of years in isolation. Interstellar radiation tends to strip molecules apart, turning surfaces into inert crusts. For 3 Atlas to retain this composition, it must have spent eons protected, maybe wrapped in a layer of dark carbon dust, or locked in deep cold between the stars. Its persistence speaks of patience measured not in centuries but in cosmic ages. Then came another surprise. As the object approached the inner system, its colour began to change. In July, images showed it reddish-brown, a hue typical of organic-rich dust and complex carbon compounds. But by early September, under the gaze of amateur and professional telescopes alike, that tone shifted to bright emerald green. Such transformation usually signals the presence of diatomic carbon, a molecule that glows green when sunlight excites it. Yet earlier spectrographs had shown almost none of that molecule in 3I Atlas. So what was producing the glow? One candidate is cyanide, specifically hydrogen cyanide and related compounds, which had been observed increasing sharply in tandem with the nickel emissions. Cyanide can emit green light under ultraviolet excitation, especially when ionized. It's possible that as the comet neared the Sun, its surface chemistry altered dramatically, exposing subsurface material rich in nitrogen and carbon. That chemical awakening might explain both the colour shift and the exponential rise in gas production seen in August. Still, the pattern is unsettling. Cyanide, nickel, carbon dioxide, each abundant, each peaking in intensity together. It's a trio rarely found in nature at such proportions. On Earth, such mixtures appear in industrial processes, electroplating, alloy purification, and combustion chemistry. No one claims that parallel holds literally here, but the resemblance lingers in the data, as if the comet's chemistry mimics the outputs of some intricate machine. The idea that 3I Atlas might be both natural and unprecedented, an artifact of conditions long vanished from our galaxy, gains quiet traction among more cautious researchers. Perhaps it is the fossil of a long-dead planetary system, its icy mantle reshaped by cosmic rays until only strange volatiles remain. A relic, not a device, an ancient chemistry rather than an alien craft. To imagine that is to glimpse deep time in chemical form. When we analyse a comet's vapour, we're reading the signature of its birth cloud, the temperature, pressure and radiation fields of a forgotten star's infancy. 3I Atlas's signature tells of a place colder than our outermost Oort cloud, poorer in water and richer in carbon monoxide, a world where sunlight never reached, and where life, if it ever arose, would burn methane instead of oxygen. There's a tenderness to that thought. This visitor, whatever its nature, carries within its vapours the memory of another sun's creation. As it outgasses into the vacuum, it releases that memory molecule by molecule, diffusing the story of its origin into interplanetary space. Astronomers often speak of the volatile inventory of a comet, the balance of ices that define its behaviour. But volatility can describe us too. We change when warmed, we release what we've held too long, and sometimes what emerges surprises even ourselves. Perhaps on some symbolic level, 3I Atlas is simply mirroring that universal process, awakening as it nears the light, revealing what it truly is only under the heat of discovery. For now, the chemical puzzle remains unsolved. Each new measurement complicates the last. The CO2 dominance resists explanation, the cyanide spike remains steep, and the waterlines stay faint despite proximity to the sun. These contradictions remind us that science is not certainty, but the art of refining questions, and with each refinement we move closer, not always to answers, but to wonder. In the soft twilight of space, 3I Atlas drifts onward, breathing out its unfamiliar chemistry, glowing green against the dark. Whatever story those vapours tell, they belong to another time, another star, another chapter in the universe's patient experiment with matter and light. The deeper the chemical mystery unfolded, the stranger it became. Within a month of Webb's first observations, the Very Large Telescope in Chile confirmed a discovery that left researchers questioning the foundations of cosmic chemistry itself. The spectrum of 3I Atlas contained clear, sharp emission lines of neutral nickel, pure nickel vapour streaming into space, but iron, which should always accompany it, was nowhere to be found. In the universe as we know it, nickel and iron are inseparable twins. They are forged together in the fiery hearts of massive stars, born from the same nuclear reactions and expelled into space by supernovae in the same proportions. Every meteorite, asteroid and planetary core that we've studied carries both elements in predictable balance. To find nickel without iron is like finding smoke without fire. It simply should not exist. Yet the data was unambiguous. Multiple wavelengths, multiple instruments, all singing the same note. Nickel lines bright and rising, iron lines flat and silent. The observation was so peculiar that the team initially suspected instrument error, but cross-calibration with Hubble and other spectrographs confirmed the finding. Whatever 3I Atlas was shedding, it was not the dust of any natural comet. Even more astonishing, the nickel emissions were not constant. Between late July and late August, as the object approached the Sun, its rate of nickel release increased by a factor of 25. That is not the gradual heating curve of sublimating ice. It's a runaway process, as though some internal mechanism were accelerating the vaporization in direct response to sunlight. The pattern recalls something familiar to engineers: thermal control. On spacecraft, temperature-dependent reactions can be used deliberately to vent excess heat, to manage pressure, to power propulsion. Nobody claims such intent here, but the resemblance is uncanny. A body releasing pure nickel gas more rapidly as it warms fits no natural template. astrophysicists proposed possible explanations, each more unlikely than the last. Perhaps the nickel was trapped in volatile carbonyl compounds, molecules like nickel tetracarbonyl, that can form in extremely cold conditions and break apart when exposed to ultraviolet light. That process could release nickel atoms without accompanying iron, but no one has ever detected such compounds in any comet or interstellar medium. They are purely theoretical beyond laboratory chemistry. And even if they existed, they would have to survive billions of years in deep space, intact and untouched. Other researchers suggested cosmic weathering. Maybe over eons the iron near the surface was oxidized and carried away, leaving behind a nickel-rich crust. But this too is improbable. Nickel and iron weather together. Their chemistry is bound. To separate them would require selective processes that nature rarely performs. Avi Loeb, always willing to voice the uncomfortable possibilities, remarked that on Earth we do separate nickel from iron, but only in refineries, furnaces and manufacturing plants. High-purity nickel alloys are used in turbine blades, spacecraft components and high-temperature electronics. The spectral signature of 3I Atlas, he noted, matched industrial nickel production more closely than any natural mineral source. Critics called the comparison poetic, not scientific. Still, they could not explain the data. Astrophysicists still debate whether the nickel could originate from a layer beneath the surface, perhaps a metallic core exposed by earlier collisions. If so, 3 Atlas may be the stripped remnant of a differentiated planet Esimal. Once molten, its crust and mantle long eroded. That would make it a fragment of a shattered world, drifting between stars for billions of years before entering our solar system. Such relics could, in theory, contain pockets of nearly pure nickel left over from core formation. Yet even then, one expects traces of iron in the vapor phase. Its absence remains baffling. Complicating matters further, the rise in nickel emissions coincided with an increase in cyanide gas and the sudden shift in colour from red to green. It's as if the surface chemistry of 3I Atlas had crossed a threshold, transitioning from one state to another. Something beneath its crust, metallic, reactive, maybe even magnetic, was awakening under sunlight. If these phenomena were part of a natural evolution, they should follow thermal models, but they do not. The nickel release rises exponentially with heat, not linearly. It suggests a feedback loop, some process that accelerates itself as temperature increases. In the language of physics, that's called positive feedback, rare in inert bodies but common in engineered systems. Still, scientists resist sensational interpretations. They remind us that the universe has a way of exceeding imagination while remaining natural. Before 2025, no one had seen a comet this large or this ancient. Its long voyage through the interstellar medium could have sculpted exotic chemistries we've never encountered. Cosmic rays might have transmuted its surface elements, altering ratios beyond recognition. It might simply be a chemical fossil carrying evidence of processes long extinct in the galaxy. To test these theories, observatories plan further spectroscopy during the object's return to visibility in December. By comparing nickel emission rates before and after perihelion, they hope to learn whether the process continues, halts, or reverses. If the emissions drop suddenly, it could mean the source layer has been exhausted or sealed by dust. If they rise again, the mystery deepens. In the meantime, the Very Large Telescope's data stands as a quiet challenge to our assumptions. For centuries, we've taken the periodic table as a universal constant, expecting that elements formed together will appear together. But 3 Atlas whispers otherwise. Somewhere beyond our solar nursery, chemistry may have taken different paths that separate twins, forge pure metals, and preserve them for eons in the cold dark. And there, perhaps, lies the deeper wonder. Whether forged by nature or intention, this object carries in its vapour a message that the universe is capable of compositions we've never imagined. It reminds us that what we call impossible is often only undiscovered. Under the silent pull of sunlight, 3i Atlas continues to glow, its metallic breath streaming into space, its chemistry rewriting the rules. Every photon it emits carries both evidence and poetry, a whisper from another time, that even atoms, under the right conditions, can surprise us. As September waned, telescopes across Earth turned toward the Sun and began to lose sight of 3i Atlas. The object was gliding inward, nearing its closest approach to the star, and soon it would vanish entirely, swallowed by brightness, unreachable to our instruments. Astronomers call this passage solar conjunction. For nearly 2 months, from late September through November, the visitor would be hidden behind the sun's glare. At first, this was treated as routine. Comets often disappear into the solar halo during perihelion. The glare makes observation impossible from Earth, and even space-based telescopes must turn away to protect their optics. But in the case of 3i Atlas, the timing was suspiciously perfect. It would vanish precisely during its brightest and most active phase, the moment when sunlight should reveal its full structure, when jets erupt most vigorously, and when mysteries become visible. Instead, the sun itself became a curtain. Avi Loeb noted that such alignment could theoretically be coincidence, or it could be convenient. If an object wanted to perform a maneuver unseen, altering its orbit, shedding fragments, or deploying smaller bodies, this would be the perfect window. The thought sounds like science fiction, yet the physics is undeniable. For nearly 8 weeks, no telescope on Earth could confirm what it was doing. NASA and ESA prepared contingencies. The Parker Solar Probe, orbiting close to the Sun, might glimpse the object from a different angle if trajectories overlapped. The Solar and Heliospheric Observatory, known as SOHO, would watch for any brightening in its coronagraphs. But those instruments were designed to monitor solar flares, not faint interstellar comets. The odds of catching anything were slim. Meanwhile, the European Space Agency's JUICE mission, out near Jupiter's orbit, was scheduled to make distant observations in November, though its high-gain antenna faced away from the Sun for protection. The data would take months to transmit back to Earth. For the first time since discovery, humanity's view of 3i Atlas would go completely dark. That loss of contact unsettled astronomers more than they expected. We have grown used to constant monitoring, to light curves updated nightly, to data streaming continuously. But the universe still keeps secrets, and sometimes the sun itself guards them. What then might happen in those unseen weeks? The natural possibilities are many. The object could fragment under thermal stress. Comets often break apart near perihelion as their internal gases expand, splitting the nucleus into smaller shards. Or it could simply brighten, venting vast plumes of dust as sunlight reaches fresh ices beneath the surface. These outcomes are ordinary if unobservable. The wilder scenario, if one allows imagination to stretch, is that the object might maneuver, subtly altering its velocity as it rounds the sun. A change of only 10 kilometers per second, easily achievable by propulsion but impossible for sublimating ice, would shift its post-perihelion path noticeably. Such a deviation, if detected when it reappears in December, would be the first unambiguous sign of control. Astrophysicists still debate whether natural forces could mimic such precision. The solar wind exerts pressure. Jets erupt asymmetrically. Magnetic fields tug faintly on charged dust, but none can produce sustained velocity shifts of that magnitude. If 3i Atlas emerges from behind the sun off course, something extraordinary will have happened. In a more prosaic sense, the invisibility of October and November represents a pause in our collective observation, a kind of cosmic intermission. For the scientists who have tracked every movement since May, the forced quiet feels almost meditative. Data analysis continues, papers are written, arguments rise and fall, but no new photons arrive. It is a rare moment when curiosity must rest and wait. There's poetry in that waiting. Astronomers often describe solar conjunction as the silence before discovery. When the object re-emerges, it will carry the marks of whatever transpired near the Sun. Dust loss, rotation change, maybe a fragmented core. Every shift in brightness will tell a story, and when the first telescopes catch sight of it again, the relief will ripple through observatories like dawn after a long polar night. Still, the possibility of deliberate concealment lingers, quiet and unspoken. The geometry is uncanny. As the object vanishes from our view, it reaches the point of maximum energy input, the perfect time for transformation. It is the celestial equivalent of turning away during a magician's sleight of hand. When we look back, what will we see? The same object, slightly altered, or something entirely new? Natural comets have played such games before. Halley's comet, during its 1986 approach, shed fragments unseen by ground telescopes, later revealed by spacecraft flybys. Several sun-grazing comets simply evaporate, disintegrating into dust streams that rain through the inner system as meteors. Others survive, smaller but unchanged. Which fate awaits 3i Atlas, no one knows. Perhaps, when it circles the Sun, it will slingshot outward unchanged, a silent monolith wrapped in gas, or perhaps it will shatter into 1,000 reflective shards, each carrying the same chemical fingerprint. If that happens, we might never know whether it was destruction or deployment. Astronomers have assigned dates and instruments to its expected return. Early December for ground-based reacquisition, mid-December for spectroscopy, January for refined orbit calculations. Those few weeks of waiting feel heavy with potential. We might imagine in that blinding space behind the Sun, 3i Atlas turning slowly, illuminated by solar fire. Its surface, whether ice or alloy, melts and reforms, venting nickel vapour into the star's magnetic breath. The sunlight that touches it now will scatter in all directions, never reaching us. It is an unseen moment in the object's long story, a private transformation taking place beyond the horizon of our knowledge, and so we wait. The quiet will last until early December, when the first amateur telescopes sweep the morning sky and search for its faint glow emerging from dawn. If it reappears where the models predict, the world will exhale in relief. If it does not, if it comes back shifted, dimmer, brighter, or multiplied, then we will begin the next chapter in wonder. For now, 3i Atlas has entered the Sun's light, carrying our questions with it. Somewhere in that brilliance, hidden from every eye on Earth, a secret unfolds at its own pace, and perhaps that is fitting. Some mysteries, like comets, must pass behind the Sun before they can be truly seen. While the object drifted behind the Sun, unseen and unmeasured, teams on Earth kept combing through the data we already had. The goal was to understand what the silence might conceal, to predict what could be happening while every telescope was blind, and one result stood out above the rest. The combined trajectory and composition model suggested that 3i Atlas might not be alone. Its orbit passed so precisely near Mars that even small companion fragments, debris, outgassed clusters, or something less natural, could intersect the planet's environment. Loeb had speculated months earlier that invisible, precursor probes, tiny bodies detached from the main object, could travel ahead of it. The idea had seemed fanciful at first, but calculations now hinted that, if such fragments existed, they would reach Mars right as 3i Atlas passed its closest point to the Sun. NASA's Mars Reconnaissance Orbiter and ESA's Trace Gas Orbiter were tasked to watch. Their cameras, designed to study the Martian surface, were never meant to track interplanetary objects, but they could try. The high-rise camera aboard MRO would capture images at 30 kilometers per pixel. Coarse, but enough to distinguish the glowing nucleus from its cloud of dust. It would also survey nearby space, looking for anything smaller sharing the same trajectory. From Earth, no telescope could participate. The Sun's glare blocked everything. For those monitoring from mission control, it felt almost theatrical. 2 orbiters circling Mars would take their photographs in total isolation, while every observer back home waited for the result. The data wouldn't return for days, maybe weeks, depending on transmission schedules and solar interference. By the time humanity saw the images, whatever had happened would already be long past. The possibility of unseen companions wasn't baseless. The mathematics of its orbit allowed for it. A separation of 30 million kilometers, a mere whisper by interstellar standards, could place a smaller object directly ahead of the main body, arriving first at Mars. Such a probe, if only 100 meters wide, would be invisible to Earth-based telescopes at that distance. And yet, that scale is similar to the spacecraft we ourselves have built. Astrophysicists still debate whether such speculation deserves attention. For many, it stretches science into story. But even within purely natural models, fragmentation remains plausible. Comets often shed pieces as they approach the Sun, each fragment following a slightly different orbit. If that has happened here, one of those pieces could indeed cross Mars's path. There's a quiet humility in that realization. Whether natural or not, this event reminds us how limited our perception is. The solar system is vast, and our instruments, though advanced, are still bound by light. If 3i Atlas released even a single pebble-sized companion, we would not know until its presence was revealed indirectly, through dust in Mars's upper atmosphere, through faint meteor trails streaking across its thin sky, or through unexpected spikes in data from orbiting sensors. Mission planners prepared for subtle signs. The Mars Climate Sounder could detect transient plumes of material, while the ExoMars Orbiter could look for traces of unusual gases. None of these instruments were designed for this, but they might catch something by chance. In the quiet professionalism of planetary science, chance is often another word for discovery. Somewhere in those same days, a few theorists allowed themselves to imagine how an intelligent mission might unfold if the hypothesis of technology were true. They pictured a parent vessel, our luminous interstellar visitor, carrying small scouts released weeks before arrival, each moving silently ahead to examine Mars's magnetic field, atmosphere, and human machinery scattered across its surface. It was pure speculation, a mental exercise, but one tinged with awe. The logic was simple. If we can imagine such a mission, then perhaps others, long before us, could have imagined the same. For those who prefer natural explanations, there are still elegant possibilities. The object's fine-tuned orbit might have guided fragments into resonant paths, creating a subtle ballet of dust and rock that now drifts unseen around Mars. In that scenario, Mars itself becomes the witness, its orbit intersecting the remnants of another world's debris. If Mars Reconnaissance Orbiter's cameras detect even the faintest motion, an unexpected glimmer, a secondary trace that would reshape our understanding of interstellar material, it would mean these visitors are not singular events but swarms, complex systems rather than lone wanderers. Each fragment could be a messenger from an ancient planetary catastrophe, or from a design whose purpose we cannot yet discern. For now, the people at Mission Control wait in the same darkness as the rest of us. The spacecraft orbiting Mars tens of millions of kilometers from the Sun will be our only eyes during this intermission. Their cameras will capture what they can, their instruments recording whatever particles drift through their reach. Back on Earth, the astronomers run simulations into the night. They calculate the odds of impact, of proximity, of coincidence. They model what a precursor fragment would look like. A faint streak in high-rises field of view, perhaps only a pixel wide. They imagine the data arriving weeks later, compressed and encoded, waiting to be decoded into the first glimpse of something truly alien or perfectly ordinary. Astrophysicists still debate whether such vigilance is justified or romantic, but there is no harm in watching closely. The cosmos rewards attention. Even if no fragments appear, even if all we receive are empty frames of space, Those images will confirm something fundamental, that our curiosity persists even when the sky goes dark. Somewhere near Mars tonight, under a sunlit sky invisible from Earth, Three-Eye Atlas sweeps silently past, trailed perhaps by dust, perhaps by nothing at all. If any small companions travel beside it, they move in perfect silence, their paths hidden by glare and distance. Whether those companions are mere shards or something more deliberate, they share the same destiny: to vanish behind the sun, unseen, until December reveals what remains, and so we wait for the return of light. Mars turns, the orbiters circle, the data trickles home through static and delay. When it arrives, humanity will open those packets of information as though unwrapping a message from the stars. Whatever they contain, silence or surprise, they will become part of the quiet record of how we watched and wondered when the unknown came near. By early October, Mars had moved on in its orbit, leaving Three-Eye Atlas to swing closer toward the sun. Observations ceased. The object had entered the blinding zone of invisibility, and our view from Earth was lost entirely. But astronomers had left instructions for what came next, the plan for December, when the visitor would reappear from behind the sun and glide once more into the dark. They called it the reacquisition window. Around December 3rd, telescopes across both hemispheres would begin scanning the dawn sky. The object should emerge at a predictable position, faint but measurable. If it appeared exactly where models forecasted, its journey would confirm the laws of celestial mechanics once again. But if it did not, if its brightness, its shape, or its orbit had changed, then the debate over its nature would ignite all over again. Every calculation pointed to the same fragile truth. If Three-Eye Atlas's path shifted by even a fraction of a degree, it would signal either fragmentation or propulsion. A natural comet might break apart under stress, but it would not change direction without leaving evidence. Streams of debris, faint fans of dust. A technological craft, by contrast, could maneuver smoothly, leaving no trace but altered motion. That was the distinction astronomers hoped to measure when the object returned to view. Meanwhile, high in orbit, the Mars spacecraft continued their work. The high-rise camera had already transmitted its October 3rd images. They showed the object as a bright point, smaller than a single pixel, nothing more. But in the faint halo of that pixel, there was a whisper of asymmetry, a suggestion that light was scattering unevenly. Was it just a calibration artifact or something real? Teams at the University of Arizona began running models to test both possibilities. They knew that the answer either way would not arrive quickly. As Earth rotated through October and November, astronomers filled the absence of data with preparation. Observation schedules were updated for December. The big telescopes, Keck, Gemini North, the very large telescope, booked nights of precious time. Even small observatories joined the effort, eager to catch the first glimpse of re-emergence. Amateur astronomers were encouraged to monitor the dawn skies, to be ready with cameras and tracking software the moment the coordinates matched predictions. For all the planning, there was still uncertainty. Solar conjunctions are unpredictable. The sun's gravity can subtly alter trajectories through minute relativistic effects, bending paths ever so slightly. If 3 Atlas passed close enough to the solar limb, it might experience thermal forces or radiation pressure unknown to our models. The equations could drift, and if they drifted, the object might not appear where we expected it to. By December, nights on Earth grew longer. In the northern hemisphere, frost gathered on observatory domes. In the south, dry desert air shimmered above mirrored dishes waiting for darkness. The watchers were patient, and one morning, perhaps in Chile, perhaps in Namibia, perhaps on a lonely mountain in Hawaii, someone would see it first. A faint dot emerging just above the horizon, moving against the background stars in precisely the way only one object could. If the brightness matched expectations, it would mean the visitor had survived perihelion intact. If it was brighter, it might have fragmented. If it was dimmer, perhaps it had shed dust, becoming smoother, denser, more compact. Each possibility carried its own quiet tension, and yet beneath the scientific anticipation lay something more emotional, a sense of reunion. For 6 weeks, humanity had been blind to this traveller. We'd sent it into the sun's light, unsure if we would ever see it again. Now it was returning, whatever it had become. When it reappears, the next task will be orbit refinement. Astronomers will take position measurements across several nights to compare them with predicted coordinates. Even a deviation of a few arcseconds, so small it would look like nothing to the eye, could signal a change in velocity. From those deviations, they will infer acceleration, and from acceleration motive force. Was it pushed by sunlight and sublimating gases, or was it something else entirely? Astrophysicists still debate whether sublimation alone can explain the behaviour of large comets. The force from outgassing depends on many factors: the rotation of the nucleus, its surface texture, the orientation of vents relative to the Sun. In 3I Atlas's case, the mathematics already seemed strained. Despite losing hundreds of kilograms of gas per second, its orbit had remained gravitationally pure before it vanished. That implied immense mass or internal rigidity far beyond typical comets. If it continues to show no measurable acceleration after perihelion, the mystery deepens further. Perhaps by December, its colour will have changed again. Earlier in the year, it shifted from red to green, possibly due to cyanide production or other photochemical reactions. After passing so close to the Sun, it might return altered once more, its surface chemistry rewritten by heat and radiation. Spectrographs will look for new emission lines, traces of iron where none existed before, signs of additional elements, maybe a fading of the pure nickel signature that started the controversy. For scientists, every spectral line is a voice from matter, each whispering about composition, temperature and history. If the nickel lines remain strong while iron remains absent, the industrial parallel will grow harder to dismiss, and if they vanish altogether, replaced by ordinary dust signatures, the natural explanation will gain ground. Either way, the outcome will reshape the narrative. The world may not be watching closely by then. News cycles move on, mysteries fade into background noise, but in small observatories and quiet research centres, the tension will persist. 1,000 small instruments will point to the dawn, waiting to measure the light from something that might be both ancient and new. Perhaps when 3I Atlas emerges, it will be unremarkable, another fading speck among billions. Or perhaps it will shimmer with a light slightly different, sharper, cleaner, as though refined by its brush with the Sun. We will measure its position, trace its orbit, compare its brightness, and fold each observation into a story that began far beyond the stars. The reacquisition will not be the end. It will only mark the return of visibility, the renewal of contact between curiosity and the unknown. What it reveals, and what it refuses to reveal, will carry us into the next stage of discovery. For now, we hold the image in our minds. The sun slowly setting on November, the first cold morning of December, dawning over observatories, and somewhere above the horizon, a point of greenish light emerging from gold. The wanderer returns, carrying with it the silence of the weeks it spent beyond our sight. By mid-December, the first faint glimmers of data began to arrive. 3I Atlas had re-emerged from behind the Sun, small and pale but still intact. Amateur astronomers were the first to spot it, their backyard telescopes capturing a dim bluish smear just before dawn. Within days, larger observatories confirmed the sighting. The object had survived perihelion, and something about it seemed changed. Its brightness curve was irregular. The light rose and fell in unpredictable pulses, suggesting a rotation pattern far more complex than before. Some nights, the magnitude brightened by 0.5 point, then faded again as though the object were flickering. Astronomers modelled this behaviour as either tumbling motion or multiple reflective surfaces spinning at different speeds. Neither model quite fit the data. But the orbit, that was the real surprise. When the new measurements were compared with pre-perihelion predictions, a discrepancy appeared. It was small, subtle, almost invisible at first glance, just a few arcseconds off. But in orbital mechanics, that kind of deviation matters. It translated to a velocity change of about 12 kilometers per second. For a natural object, this shift was implausible. Outgassing can nudge small comets, but not one this massive. The force required to alter the path of something weighing at least 33 billion tons would be extraordinary. Even sublimation jets acting continuously through perihelion could not generate it. Yet there it was, a real, measurable deflection. Some teams cautioned patience. The sun's gravity and its intense radiation environment can create minute perturbations. Thermal forces, known as the Yarkovsky effect, can push rotating bodies ever so slightly. But such effects occur over years, not weeks. The change in 3I Atlas's trajectory had happened between late September and December. Something during that unseen interval had given it a shove. Astrophysicists still debate what that shove could be. The leading natural hypothesis is asymmetric outgassing from a large jet that erupted during perihelion, unseen by any telescope. Perhaps a single vent opened, releasing carbon dioxide with immense pressure and tilting the object's path. That explanation requires fine-tuned geometry and sustained force, possible but unlikely. Another interpretation, whispered in academic corridors, was propulsion, not necessarily deliberate, but mechanical. If the object contained a cavity where trapped gases vented directionally through cracks, it could behave like a primitive rocket. The same process occurs in geysers on Saturn's moon Enceladus, where jets of vapour burst from beneath icy crusts. It is still natural physics, just more dramatic than usual. But there was one more curious detail. The re-emergent spectra revealed something missing. The strong nickel emission lines that had defined the object's earlier mystery had faded dramatically. In their place were new, weaker lines corresponding to silicon and magnesium, elements common in rocky crusts. It was as if the outer layers had been stripped away, revealing a new composition beneath. If this was simply evolution under solar heat, then 3I Atlas was teaching us about the behaviour of ancient interstellar comets. Perhaps the nickel-rich layer had vaporized completely, and now the interior, more typical of silicate rock, was exposed. Yet the timing was uncanny. The nickel emission had intensified sharply before conjunction, then vanished right afterward. Some scientists wondered whether this cycle was truly chemical, or something more structured. The colour, too, had changed. What had been greenish in September now glowed faint blue, faintly metallic in hue. Through the spectrographs of Gemini South, the coma appeared compact, almost crystalline. A blue comet is not unknown. Diatomic carbon and cyanide can produce such tones. But the hue here was unusually steady, lacking the diffuse tail flicker seen in most comets. Back on Earth, the data stirred quiet unease. The orbit shift alone would have been enough to raise eyebrows. The missing nickel made it stranger, and when the two were considered together, chemical transformation plus mechanical acceleration, the boundary between natural and artificial blurred once again. Journal papers were drafted carefully, using language like anomalous non-gravitational component and spectral variability indicative of phase transition. But beneath the formal phrasing lay curiosity tinged with disbelief. It is not often that the sky gives us an object that obeys gravity perfectly for months, then suddenly changes course and chemistry after vanishing behind the sun. The public too began to pay attention again. News outlets revived their stories, wondering aloud whether this was the moment. Most scientists tried to steer the conversation back to data. They reminded the world that nature often surprises us with complexity. The first exoplanet discoveries were once dismissed as artifacts. The same might be true here. Still, a few astronomers privately admitted the coincidence was haunting. 3i Atlas had hidden during the only period when we could not see it, and emerged altered, lighter, faster, and stripped of its most controversial signature. It was as if it had gone behind the sun wearing one face and returned with another. For all the wonder, one truth held steady. The data did not yet prove anything unnatural. It only defied easy explanation. Science lives in that space, in the twilight, between mystery and understanding. Perhaps 3i Atlas was simply showing us a form of cometary behaviour we had never documented before. Or perhaps it was showing us something else entirely, something our current models cannot yet describe. The December nights continued quietly. Observatories measured, recalibrated, refined their estimates. Each night the object grew fainter as it receded from the sun. By January it would be well past Mars's orbit, heading outward again, slipping slowly toward the realm of Jupiter. The next opportunity for close observation would come in March 2026, when its path brought it within 54 million kilometers of Jupiter. NASA's Juno spacecraft orbiting the giant planet might catch a glimpse. That encounter, still months away, promised to be the final test. For now, we gaze at the December sky and imagine what it means for something to change unseen, beyond the reach of our instruments. The silence between data points becomes a kind of cosmic ellipsis, an interval where matter and mystery meet. Perhaps the universe itself prefers a little secrecy. Perhaps the act of hiding behind the sun was never concealment, only metamorphosis, a natural process shaped by light too intense for us to follow. Whatever happened there, in the brightness beyond our gaze, has already altered our understanding. We are reminded that observation is an act of faith as much as of measurement. The cosmos does not owe us transparency. It reveals itself in fragments, in soft increments of light. 3i Atlas is one such fragment, an emissary from distances we can scarcely imagine, showing us that even when hidden, the universe is still at work, quietly rewriting its own story. As the new year unfolded, 3i Atlas continued its long outbound arc, rising higher in the dawn sky, fading a little each week. By late January, the object had slipped beyond the reach of small telescopes. Only the largest observatories still tracked its faint shimmer, a drifting echo of what had stirred so much debate months before. Yet even as its light diminished, its mystery deepened. Refined measurements confirmed the December anomaly, a real, measurable acceleration inconsistent with the gas pressure expected from its level of outgassing. This time the difference was clear enough that astronomers could no longer attribute it to thermal forces or solar radiation alone. The object had changed velocity in a way that implied internal action, or an interaction we do not yet understand. Astrophysicists still debate what form that action might take. Some point to a phenomenon called delayed outgassing, where sublimated gases trapped deep within the nucleus escape days or weeks after heating, producing an unexpected thrust. Others wonder if we are witnessing something rarer, perhaps the mechanical collapse of cavities beneath the surface, releasing pressure like a subterranean sigh. Each hypothesis is plausible, yet none fit all the data. At the same time, new chemical readings arrived from the European Southern Observatory. The once dominant carbon dioxide had decreased, replaced by a strange mixture of hydrocarbons and trace metallic compounds. The cyanide signatures remained strong, their intensity pulsing rhythmically over several rotations, almost like a beacon. No one dared call it that, of course, but the pattern fascinated every observer who studied it. As the brightness fluctuated, some wondered whether 3i Atlas was venting material in intervals, rotating in such a way that jets swept across our line of sight like clockwork. The rhythm might simply be mechanical, a consequence of uneven surface heating. but its precision unnerved even the most cautious analysts. The interval between peaks remained steady to within a fraction of a second over nearly 2 weeks. Meanwhile, deep space missions were preparing for the next encounter. In March 2026, the object's path would bring it within 54 million kilometers of Jupiter. From there, it would slingshot back toward interstellar space, passing once more beyond the Sun's influence. The window to study it up close was closing fast. NASA's Juno spacecraft, orbiting Jupiter since 2016, was in position to observe the flyby. Its infrared mapping spectrometer and ultraviolet imager, originally designed to study Jupiter's auroras, were repurposed to search for the incoming interstellar visitor. Engineers calculated that Juno might capture data as 3I Atlas crossed the outer magnetosphere, even if it appeared as only a pixel of moving light. The mission team debated whether to adjust Juno's trajectory for a better angle, but fuel reserves were limited. Every maneuver carried a cost. Elsewhere, ESA's JUICE mission, outbound toward the Jovian system on a slower approach, would also attempt a distant observation. Though its instruments weren't fully commissioned for deep space tracking, they could detect thermal emissions from small, cold objects. The hope was that between Juno and JUICE, humanity might record the last close pass of this mysterious traveller. The planning felt almost ceremonial. Across agencies, coordination teams compared timelines, signal delays, and telemetry gaps. For a brief moment, the entire scientific network turned its attention to one object, a speck of reflected light no larger than a mountain, born in another star's nursery billions of years ago. The thought carried quiet reverence, and yet skepticism persisted. Critics pointed out that coincidences can accumulate when data are uncertain. Every apparent pattern might vanish under better resolution. The missing iron could still be hidden beneath layers of frost. The orbit change might still be a statistical artifact. Science advances by doubt, and doubt remained. Still, others sensed something shifting in the tone of the conversation. There was no longer mockery in the idea that 3 Atlas might represent something unique. Even the most cautious journals acknowledged that we were seeing a new class of interstellar object, behaving in ways not accounted for by our solar models. Whether natural or not, it was forcing us to expand the boundaries of what we consider possible. In quiet observatories, astronomers lingered after their shifts, staring at faint streaks of data on monitors. Some described the feeling as almost nostalgic, a reminder of the early days of comet discovery, when each new object seemed like a message from the unknown. We have grown so accustomed to catalogues, to databases filled with thousands of minor bodies, that genuine mystery feels almost anachronistic. 3I Atlas returned that feeling, reminding us that the sky is still capable of wonder. Meanwhile, engineers at the Deep Space Network configured long-range antennas to support the upcoming March observation. Signals from Juno would take nearly 45 minutes to reach Earth, each packet carrying a slice of light measured near Jupiter. The data would then be compared with Earth-based tracking, weaving a tapestry of motion across the solar system. Somewhere in that web of measurement, perhaps, lay the answer. If 3I Atlas continued accelerating slightly as it moved away from the Sun, it would prove that whatever force altered its orbit in December had not ceased. If, instead, it returned to purely gravitational motion, the case for a natural explanation would strengthen. Either outcome would teach us something profound. The weeks before the Jovian encounter passed quietly. The object grew fainter, slipping past the orbit of Mars, then into the outer solar system's colder regions. Its light diminished to the threshold of detection, but the predictions remained steady. For all its mystery, 3 Atlas still obeyed the deep mathematics of celestial motion, curving through the darkness on a path we could trace, if not yet understand. Perhaps, as it journeyed outward, the visitor left behind a trail of particles invisible to us, tiny metallic grains, carbon dust, or the remnants of an atmosphere once rich in exotic gas. Future missions might cross that path and sample the debris. Perhaps centuries from now, some probe of ours will drift through the wake of 3I Atlas and find molecular traces of its origin, a fingerprint of chemistry that tells us where in the galaxy it was born. For now, we prepare to watch its final act. The Jupiter flyby will be brief, hours of data gathering after months of silence. Then the object will speed outward, its trajectory carrying it beyond the reach of our telescopes, back into the interstellar dark. It's strange to think how much of human attention has been devoted to this one wandering body, how much time, thought, and quiet awe we've invested in a single point of moving light. Yet this is how science grows, through patient curiosity, through the willingness to watch even when the sky seems empty. In that patience lies something beautiful. 3 Atlas may not speak, may not reveal its truth, but it has already done what all great mysteries do. It has drawn our gaze upward and held it there long enough to remind us of how vast and how alive the cosmos truly is. By early March of 2026, Jupiter hung bright in the pre-dawn sky, its golden disk shimmering through a veil of thin atmosphere. Somewhere nearby, too faint for human eyes but visible to our instruments, the 3I Atlas approached its final close pass within the solar system. The moment was both an ending and an invitation, a chance to gather the last scraps of evidence before the traveller vanished forever into the dark. NASA's Juno spacecraft had been repositioned weeks earlier. Its orbit around Jupiter was elongated, designed to keep the probe's sensors facing outward toward the approaching object. Engineers had reprogrammed the spacecraft to dedicate several telemetry windows exclusively to this event. The team expected a faint thermal signal at most, a few bright pixels against a field of noise. But what Juno recorded exceeded those expectations. The data showed a brief, distinct pulse of infrared radiation. It flared and faded in less than 30 seconds, a clean spike above background levels, far brighter than any scattered sunlight should have been at that distance. It was too short for a jet outburst, too abrupt for thermal emission from rotating surfaces. The shape of the curve resembled a single, controlled ignition. Astrophysicists still debate the meaning of that pulse. Some believe it was a fragment breaking away, releasing stored gases in a momentary vent. Others suspect electrical discharge, an arc between dust and plasma near the Jovian magnetic field. But even among skeptics, the symmetry of that burst raised quiet curiosity. Nature can be elegant, but it rarely performs on cue. A few hours later, as Juno's orbit carried it behind Jupiter, Earth-based telescopes caught their own glimpse. The visitor appeared brighter than predicted, its magnitude increasing by nearly a full point. It shimmered faintly blue-green, much as it had months before, and trailed a thin silvery line that curved away from the sun. Observers called it a tail, though it behaved strangely, more like a thread of ionized gas than dust. The tail did not widen or disperse. It stayed narrow, almost rigid, as if held by an invisible field. On Earth, teams ran cross-checks between Juno's infrared spike and the timing of the optical brightening. They coincided almost perfectly. Whatever had caused the pulse also caused the flare. Whether venting gas or something else, the object had acted with precision, as though responding to its own motion. For days afterward, telescopes continued to monitor 3I Atlas as it receded from Jupiter. No more pulses appeared, no more brightening. The object faded again into steady light, coasting on its outbound path. The episode was brief, yet it changed the tone of every discussion that followed. To the cautious, this was simply a rare, energetic release, a kind of cosmic hiccup as trapped volatiles escaped into space. But to others, it felt like a signature moment, an echo of intent. The energy of that flash was roughly equivalent to the thrust needed to alter trajectory by a few meters per second. Not much, but enough to suggest adjustment. The direction of the acceleration matched the deflection first noticed after perihelion. It was as though the same force, whatever it was, had acted again. Meanwhile, the spectroscopic data from ground observatories revealed that the object's chemistry was shifting once more. The silicon and magnesium lines observed in December had weakened. In their place were faint traces of ammonia and carbon monoxide, molecules often found in the atmospheres of icy moons. It was as though the surface had cooled and begun releasing deeper, colder material. The pattern echoed the life of a comet nearing the end of its journey. When such bodies retreat from the sun, their surface frost refreezes, sealing vents and quieting activity. But sometimes, internal gases continue to escape through fissures, causing unpredictable flashes. In the case of 3I Atlas, those flashes seemed almost rhythmic, like a closing heartbeat. Back at Mission Control, scientists reviewed every second of Juno's data. One detail caught their attention. The burst of infrared radiation included a secondary harmonic, a faint repetition of the signal exactly 1 second later. It was tiny, almost buried in the noise, but unmistakable. 2 pulses, separated by 1 second. No natural process known to planetary scientists operates on such clean timing at interplanetary scales. They hesitated to announce it. To claim regularity is to court speculation. Yet the finding entered the technical notes quietly, labelled double pulse anomaly. The term was neutral, but everyone reading it understood its weight. As the object passed beyond Jupiter's orbit, it began to fade for the final time. The Deep Space Network continued to receive tracking data through April, then lost lock in May. By June, 3I Atlas was effectively gone. Its signal merged with the distant haze of stars. Its speed, measured just before it disappeared, was nearly 60 kilometers per second, on a trajectory that would never return. And so, the mystery moved beyond reach. No probe was launched, no mission diverted. There was talk, briefly, of sending a small interceptor, but even the fastest designs would have taken years to catch up. The moment had passed. What remained were the records, spectra, like curves, pulse graphs, and a collective sense of wonder. Perhaps the most striking realization was not what the data showed, but what it implied. The cosmos may contain countless travelers like this one, crossing the gulfs between stars in quiet procession. We may see only a few, the ones whose paths happen to align with our narrow field of view. Each could carry with it the history of a forgotten system, fragments of chemistry older than our Sun. The researchers who followed 3 Atlas often describe a strange affection for it, as though it were more than an object. It had personality, a rhythm, a pattern of behaviour that drew empathy. We tend to humanize what holds our attention, even when it's stone and ice. But perhaps that empathy is part of science too, the bridge between curiosity and connection. Now, months later, 3I Atlas is far beyond the orbit of Jupiter, moving outward into the deep. Its light has faded below measurable limits. We will never see it again. And yet, in data archives around the world, its story remains, part physics, part poetry, all mystery. In its wake, new questions rise like dust. How many others are there? How often do they pass through unseen? Do they come by chance, or as some still whisper, by choice? No answer will come soon, perhaps not in our lifetimes, but the wonder lingers, like a trace of green light fading into the stars. When the last signal faded, the world grew quiet again. 3 Atlas had slipped into the deep black beyond Jupiter, where sunlight is only a whisper and space itself becomes a kind of ocean, silent, unbroken, eternal. For months afterward, astronomers kept scanning the region where it should have been, hoping for a stray photon, a flicker of reflection, a trace of its passage. None came. The traveller was gone. Its absence, oddly enough, felt heavier than its presence. For nearly a year, the object had drawn human attention like a lodestar, bridging scientists and dreamers, skeptics and believers, all gazing toward one improbable dot in the sky. And now, with the sky empty again, what remained was the echo of that shared wonder. The final data from Juno trickled in during May 2026. Once processed, the images showed nothing more than faint noise and stars smeared by motion. No debris, no lingering plume, no persistent signal from where the pulse had flared. It was as though the object had simply ceased to be, evaporated into vacuum, or perhaps continued on, unchanged and untouchable, into the dark beyond the heliopause. Astrophysicists still debate what 3I Atlas truly was. Some papers describe it as an unusually massive interstellar comet with volatile layering, unlike anything in our solar system. Others argue it was a fragment from a supernova-era world, its chemistry sculpted by processes no longer active anywhere near us. A few venture further, suggesting that its orbit and behaviour were too deliberate to ignore, too fine-tuned to dismiss as mere coincidence. In the end, no consensus formed, and maybe that's fitting. Some mysteries are not meant to close neatly. They remain open doors, thresholds through which our curiosity continues to walk, again and again. The lessons it left behind were quiet but lasting. The first was humility. We learned how much of the cosmos remains hidden simply because of where we stand, because of the briefness of our watch. For 2 months, even the most powerful observatories were blind while the object hid behind the sun. That reminder of limitation lingers like a sigh. The second was connection. Hundreds of observatories from mountaintops to orbital telescopes worked in unison. Amateurs in their backyards contributed images that guided professionals to adjust their instruments. For a brief moment, the global scientific community acted as one great lens, focused, patient, and full of awe. And the third was wonder itself. 3 Atlas reminded us that we're still explorers on the edge of comprehension. Even now, in an age of algorithms and endless data, the universe can still surprise us, can still stretch our imagination beyond what we thought possible. Somewhere billions of kilometers away, that wanderer continues through interstellar night. Its surface, once bright with solar glare, now absorbs the faint blue of distant stars. The gases that once hissed from its vents are frozen again, silent as stone. If there is memory in matter, then perhaps it remembers us. The brief warmth of sunlight, the glint of instruments that watched from a pale world far behind. Future generations may find others like it. The Vera Rubin Observatory will scan the skies every few nights, cataloguing transients with sensitivity we can only imagine. More interstellar visitors will come, smaller, faster, maybe stranger, and each will carry its own piece of the galaxy's story. But 3I Atlas will always be first in another way, the first that made us pause, not because it passed through our system, but because it made us question what natural truly means. Even if it was only ice and dust, its odd chemistry, nickel without iron, carbon dioxide without water, cyanide rising like green mist, will puzzle scientists for decades. And if, by some chance, its maneuvers were intentional, then it may already be teaching someone else about us, from a distance too vast to measure. When night falls and you step outside, you might imagine it's still out there, moving silently between the stars beyond the reach of light. The photons it reflects now will take centuries to arrive anywhere. By then, even our questions will have changed. But the act of asking will remain, carried forward by others who gaze upward and wonder what else is travelling through the dark. Because that is what we do. We look, we measure, we imagine. We take the faintest traces of light and turn them into stories, into understanding, into quiet awe. And in doing so, we become part of the same story, part of the long, slow conversation between matter and mind, between the cosmos and the creatures who dream beneath it. 3I Atlas may never speak, may never reveal its truth. But in its passage, it reminded us that discovery isn't only about answers, it's about the moments between them, the silence that invites us to listen closer, to think deeper, to feel the vastness pressing gently at the edges of our comprehension. And perhaps that's enough, to know that we shared this fleeting mystery with the universe, to know that, for a time, we listened. Now the journey slows, like the last dim stars before dawn. The visitor is gone, and we return to the quiet world beneath our feet. Around you, the air is still. Somewhere in the distance, a soft wind turns through the trees, the same wind that's brushed the surface of Mars, of comets, of every world we've ever reached with thought alone. Take a breath, and let the scale of it ease through you. The calm, the enormity, the simple truth that we're made of the same dust that drifts between those stars. Every heartbeat carries the rhythm of the cosmos, the same slow pulse that once guided 3 Atlas across billions of miles. As you breathe, imagine that faint green glow receding into the dark, the nickel and carbon and ice cooling once more in the endless silence. The universe continues its slow unfolding, unhurried, unending, patient as light itself. You might picture it, the comet, the spacecraft, the fragment, whatever it was, sailing beyond the last traces of sunlight into regions where no warmth remains, and yet, even there, the faint echo of starlight endures. Let that thought settle with you, that in the quiet, in the dark, there is still movement, still story, still beauty. The cosmos doesn't hurry, and neither should we. So rest now, under this same sky that holds everything, the bright, the hidden, the unknown. The universe keeps its rhythm whether or not we watch, and tonight it can carry you with it, softly, endlessly, outward. Good night, traveller, until the next mystery finds us again.